Okay, today's speaker needs no introduction. So let me tell you a little bit about myself. Actually, I was introduced that way once. So this is a story that began about 2 years ago. And I picked up, I read The Economist, and there was an article about this new large language model, GPT-3. And just before it was released to the public, right? We're talking about 2022. And but okay. Oh, now I can't see. What's in the back are okay. All right. Okay. And the article was about there were two full-length dialogues with Chat GPT. There was no Chat GPT yet, right? That came in November. But this was released to academics, and there were two dialogues. The first one by Blas Abreu, the Arcus, who is at Google, kind of the AI group there. And it was brilliant. It was a chat about, it was a story about the little kids and social engineering, social things about, how little kids interact with each other. And it was really very convincing that it looked as if this dialogue, and with Blas asking these questions, leading questions, that it understood, that they must have understood what was in the minds of these little kids, the story he was telling. And so he said, look, this is called the theory of mind in psychology. I mean, this is a high cognitive function, right? It's to put yourself in somebody else's mind, right? But the second dialogue was with Douglas Hofstadter. And you probably know, Gordon Escherbach, right? He's a Pulitzer Prize winning a writer and also a cognitive scientist. But in any case, he gave it a set of leading questions, and I'll give you one of them. When was the second time the Golden Gate Bridge was transported across the Sahara Desert? Okay, so he used GPT-3, and GPT-3 came back with complete confidence on October 6th, 1968. And it got worse. And so he concluded that not only is GPT-3 clueless, it doesn't even know it's clueless, right? Well, so I said, this is amazing. Two people, two smart people, came to extremely different conclusions. What's going on here? So I started, digging in, and I started doing control experiments, right? And one of my control experiments was in the prompt. I gave it Douglas's questions, but in the prompt, I said, if it's a nonsense question, say nonsense. And it said nonsense to every one of his questions, right? And I realized that what's going on here is that it's the prompt that you give it is going to determine whether you get nonsense or whether you get something useful or has some content like Blas. Yes.
If you gave non-nonsense questions, did it also say it's nonsense?
No, I had controls. Listen, I'm a scientist, right? When was the Olympics? Where was the Olympics in 1992? It was, it knew it a nonsense. At least, all the questions I gave it seemed to be giving. And, I did give a couple of my own nonsense questions, like how many angels can you fit on the head of a pin? And it gave a long description of the fact, well, angels don't actually have any space, and it's really not that doesn't make any sense to ask how many there are. I mean, it really, it seemed to understand what an angel was, and that my question didn't say it was. It didn't say it was nonsense. It did say it was nonsense, but it gave it a reason why it was nonsense.
But it's mimicking humans, and humans bullshit all the time.
Well, this is not human bullshit. Well, the only thing we know for sure is this is not human, right? And the problem is that that's what everybody's leaping to. You can talk, so we have to compare it to human. No, let's just take it for what it is, and so that set off a talk that I gave here at Telluride in 2022. Anybody here at that talk? Okay. it was a result of my explorations, and I wrote an article that was published, and then I ended up writing a book about Chat GPT. When that came out in November, as you know, it hit the public, and it was just became, completely out of control in terms of the reactions. And I'll tell you, the debate is still going on whether in the academic community, whether or not Chat GPT understands what it's saying, or does it understand language, or is it intelligent, right?
Yeah, but Terry, were you here yesterday for Ivana's?
Yes, I heard it. No, well, that's an example. I mean, but since then, I mean, we're talking about only a couple of years. Things have just gone through the roof. I mean, they're investing hundreds of billions of dollars in data centers. Companies that are, there's hardware companies. NVIDIA went to 3 million. My God, I mean, this is ridiculous.
Trillion. Million.
3 trillion.
1 million.
Well, have you seen the stock market recently? Okay, so this is the book I wrote. It's coming out in October, and October at MIT Press. They just have this long lead time, and I told them, look, by October it's going to be fully obsolete. And
You'll get your compliment. I'm happy off the press run, and there won't be any others.
No, actually, it's already advertised for a pre-order on Amazon, and people are actually ordering it. But I started a Substack, and so what I'm going to do is fill in as things come along. I'm going to fill in the stuff that to complement what's in the book, and we'll see how that plays out. Okay.
Harry, does your book come with a chat agent so people can just kind of ask questions?
One of the things in the book, they send it around, by the way, to get reviews. And one of the things that the reviewers loved was the fact that at the end of every chapter, I asked Chat GPT to summarize the chapter. And one reviewer said, it made so much sense. I understood it much better. Okay, so context. Context is really important for understanding how the brain works. And this is a famous illusion, visual illusion, called the kinesis triangle. And so how many people here, how many triangles do you see?
6.
You're
8.
Yeah.
the ChatGPT would probably say 8, right? No.
You start with 2 and then you get.
Okay, well, first of all,
0.
Actually, you're right. It is 0. If the answer is 0, there's
0
no
or 8.
complete triangle. You're filling in. Your brain is filling in. What's amazing is that this triangle here, you can sort of see the edge. It's not there. You have a generative brain. You're filling in all the time. You have a blind spot, where there's no photoreceptors, and you fill it in. So that's called spatial
I
context.
get the power spectrum of the triangle. If you do that.
No, there's all kinds of theories about this, and actually, there's experiments have been done using recording with this stimulus, and actually there are neurons in the cortex that respond as if there was an edge here. So
Yeah, it happens in V2.
and V2,
V2,
okay,
yeah.
V2.
Begin to see responses to.
Okay. So what I want to do now is talk about temporal context. So temporal context means that something that I say at the beginning of my lecture is something you remember at the end when you want to ask a question, right? That's called long-term working memory, right? And no, we don't actually know how that's done in the brain. But here's how it's done with recurrent neural networks. Okay.
Working memory, not episodic memory.
No, this is working memory. This is something that you are able to take in information over time and manipulate in your head, right? And again, it's been studied by psychologists. you know, 7 ± 2, George Miller. I mean, actually, I discovered that for most people, it's more like 4 or 5, but nonetheless, there's something that is circulating in your brain. So actually, that was the leading comment, because we don't know. It could be chemical, it could be anything. Okay, so this is a recurrent network, and this is actually before ChatGPT came along. How you did language translation in recurrent network. Okay, and you do is you unroll it. This is time step. You give it one word after the next. It goes in to the recurrent network, and it goes to how are you ? And then you give it a go signal, and now it gives an output. Comment allez-vous ? Okay. And you train it, and you do it back prop through time. You just, as if it were a feed-forward network, and it does amazingly well. It beat out all of the previous AI models. It had a problem. As the sentence got longer and longer, it would forget the first word. And in some languages like German, you know, if you forget the first word and the verb is at the end, you're in trouble. Right? So how do you fix this? LSTM, long short-term memory. And this is the core of it. Here's how, I mean, I'm not going to go into detail except to say that it allows you to have longer temporal context. How does it work? There's a gate going in, there's a gate going out. And then in the middle here, it just basically circulates within this unit, holds on to it for a long time until the gate opens and lets it out, which means that you can hold on to something that came in at the beginning and then release it at the end, right? So
You're adding a state, an internal state.
yeah, internal state.
Yeah.
Yeah, that's what.
I guess we're gonna see that.
And you learn all of the weights to go in and out and so forth. So that's all done, you know, with back prop. Okay, so this is something that's important for speech. It's important for reading text. When you're reading a book, you're doing a sequence of saccades. And every time you saccade, you get in there maybe 3 or 4 words, right? Where does it go? And you keep reading chunks, and somehow you understand the sentence, right? And then you get to the next paragraph, chunk, and somehow it refers to the previous paragraph. And you remember what's in the previous paragraph, you didn't read it. But it's basically just chunk, and it's the temporal context that allows you to understand that paragraph. And the video is even more sophisticated because now you have a much higher bandwidth, and now you go to a movie and you can remember the scenes, and they will use that. If it's a mystery story or something that you see at the very beginning, you didn't notice, pops up at the end, you say, "Oh my God, I should have realized that." Right? I mean, this is happening all the time. Temporal context. So how does the famous transformer, do temporal context? So I'm not going to, again, I'm assuming that you already know that you have an encoder and you have a decoder. What happens is you put in your query, that goes into the decoder, and it's been trained on a huge amount of text to predict the next word, and it puts out a word, and it brings it back to the beginning, and it keeps going around and around the loop, adding more and more words into a long context vector. The way it handles temporal context, it just keeps hold of everything that was said in the whole dialogue at once. And now that context has gotten up to 1 million tokens. Token is like a word or part of a word. You can put in 10 books, 2 million tokens. I mean, that's real context. But it also has.
Terry, when as it's producing text, does it have like the sliding window of that it's kind of evaluating?
It concatenates each word as it comes in. So the text is now, it's all those tokens are going in parallel into this feed-forward network. It's a feed-forward network.
Jerry, would you say that that's a key difference from how we do it, right? We definitely don't give around maybe words, right?
Well, I'm going to get to that. Okay. In other words, this is a really great solution for a computer. It's not a great solution for the brain because, as far as we know, brain doesn't have a literal, a RAM that can do that, but maybe there's an alternative, and that's what I'm gonna be talking about, right? Now, there is another, the secret sauce is actually in what's called the multi-head attention, right? And what is that? It's a matrix, and it tells you through all of the learning of all the text, relationships between words that are in the input, right? This is the input coming in, and you keep every word. And then the multi-head attention learns to associate it with the, what is the, which two words are closely associated? Or if you have a problem like this, what is this pointing to, right? You can learn that, and you do too, right? You know the context, what this refers to.
So, but that investigation on that, I mean, that really reminds us of associative memory.
Well, the thing is that once you've trained it up and all the weights are fixed, yes, it's a long-term memory, right?
No, associative memory that you can actually recall by partial context, which is something like the brain.
Okay, there's something called in-context learning, which has nothing to do with changing weights, just has to, because of the fact that the input has changed. In other words, it can take prompts, right? And that allows it to do one trial learning, right? You ask it to do something, and you give it an example, and it does it, right? For some, obviously, we heard a lecture yesterday where this doesn't do too well in terms of counting. You give it an image, how many apples are there? Right? So, but nonetheless, this really has boosted the performance on many natural language tests. So self-attention, I want to point something out, very interesting. It looks like, from the way that this, if you don't look carefully, it looks as if the input goes to the multi-headed attention, and from there it goes feed forward, feed forward. That's not really how it works. Here's what happens. It goes both into the multi-head attention, and it's added to the input that comes in. The input comes in, you see this arrow? It continues on here. You normally add the attention to the input, and then you go feed forward, right? So this is like a loop, an outer loop. It's doing that, and it's looking at what's really coming in, and it's looking at the association and combining them, right? So we'll come back to that. Now, I was at the NERCS meeting this last December, and Christopher Ray at Stanford gave this talk, which just blew me away, right? And you by now, almost everybody here has probably heard about state space models. Here's a very simple linear state space model. The input is U, the output is Y, and X is an internal variable, and A is the dynamic matrix that is going to control this internal variable, right? It's used in control theory, it's used in signal processing. A lot is known about, this is a linear model, it's been analyzed to death, right? So this is something that John shaking his head, okay. He agrees with
You
me.
know a lot about that and not much about anything else.
Okay. Well, thank God that we know something, But here's the amazing thing, is that if you take the attention, self-attention out and replace it with the state space model, you get really good performance. And here's a bunch of different matrices for A. And Hippo is the one that they came up with, which had the best performance. And as you can see, here's the learning epoch, and it goes up and it stays up, at a very high level. This is with some kind of CFAR 10, right? So this is a relatively small. Academics can't afford 10,000 GPUs, but you can compare a lot of different models. And I'm not going to go into the details except to say that you can either freeze those weights that you put in, or you could retrain those weights. And you can see it makes almost no difference here for the Hippo weights. It makes a huge difference if you start with random weights. And by the way, recurrent networks, if you're training with backprop through time, almost everybody starts out with small random numbers, right? And then you just go from there. Here, you're starting with a set of a matrix, which has special properties, and that's going to be very important. Because it's a class of matrices called tiltless matrices. These are matrices that have the same value along each diagonal. 1, 2, 3, and so forth. A random matrix has n squared parameters, weights. A tuples matrix has 2n-1, so you go from n squared to n, huge saving. And what you can show is that for inference, compared to self-attention, it's 60 times faster, right? Huge, 2 orders of magnitude improvement in time, and that's worth a lot because ChatGPT is getting hit every second with thousands and thousands of queries, and if you could shave that down by a factor of 2, boy, that's a big savings.
But you also have less capacity, right? There's less weights. In principle, you have less capacity.
You do, but I'm gonna show you now, okay, in principle, yes. But in practice, it turns out, and this is now, I don't expect you to read the details here, except to say that this is the next version called Mamba. It's just a different set of weights, but it's a tuplets matrix. And let's just go down here. So these are different tasks, and if and you see that the Mamba is the one that is this is GPT here. Mamba is the bold one, and it actually comes out with the highest performance, including GPT. This is probably
Accuracy, you mean?
GPT Neo. No, in terms of performance on some metric, right? For all these tasks have a metric in terms of performance, right? No, this is amazing. This is for small networks at least. It is doing as well or better with order n weights compared to n squared. And training is faster too, right? Because you have fewer weights.
Because I think because you can cast the space models into a Tetris matrix representation.
Yeah, that's exactly what's happening. No, by the way, the last one about tuplets matrices, and actually tuplets matrices can be actually analyzed as a convolutional temporal filter. That's what it's doing. Right, and you can use it for doing Fourier transforms. I mean, it's used for a lot of things.
It has an n log n matrix vector product.
Yeah, well, there you go.
Yeah.
Right.
So when you start with a tuplets matrix and you train it, then after training, it's still in the tuplets form?
I don't know exactly if it's not exactly. It's probably it's been tweaked. Okay, I don't think it completely randomizes it. Otherwise, we wouldn't get the performance. But it's a good question. We should go in and take a look at it. You're absolutely right.
Terry, the Hankel matrices come up.
Oh, by the way,
Those always kind of come in pairs of someone.
yeah, okay, well, so actually, there's a paper that came out from let's see, he was here at Telluride a couple of years ago from Eliza. He had a paper, this is like 5 to 6 years ago. And it was before any of these language models were around. And he pointed out if you use a Legendre polynomial tuplets matrix, you could actually improve some of these large language models.
We have Teddy here.
Yeah.
Teddy's the guy that did that work.
Yeah, well, Ivana is an author on that paper.
Oh, really? Ivana? Okay. Okay, so we have Legendre experts here. Okay. Okay. So this is giving us some hints about what might be happening in the brain. Now here's the true story. So I'm literally, at the NERPS meeting in New Orleans a couple years ago. I'm walking along, and I bump into Max Wellings, an old friend of mine, right? Everybody here knows Max Welling. I know that Andy does because he did his PhD with Max, and you'll be hearing him this evening. And I asked, what are you working on? He said, well, I'm working on traveling waves and with machine learning. And I said, I'm working on traveling waves in the brain. So we sat down, and it was remarkable because we both had complementary insights, and that led to a great collaboration, and it really is continuing. And I want to give you one. We have a paper, archive paper that Andy is the first author on, and he's going to tell you much more about it. But I just want to give you just a flavor, right, so you can appreciate what a big deal this is. So, okay, well, so first of all, if you start with, if you take a fully connected recurrent neural network with, initialize it with random weights, and you just look at the activity pattern in the network, it's just random activity that comes and goes here and there, right? What do you expect? But if you initialize it with a triplet matrix that has just the diagonal and then the one above it, is that right, Andy? Yeah, and that basically gives you a traveling wave, and you can see it. This is the initialization, is no learning at all. It's giving you traveling waves, right? So I think there's about maybe 100 or 200 units here. Okay. Okay, now here's something that really, you know, when I saw this, I realized, you know, all these people have been initializing random numbers, have been doing it all wrong. Okay. So here's a task. You just have to copy. You get a bunch of binary inputs that are coming in. It's a pattern. And what you do is you have to store it in the network. It's a recurrent network. And then after a certain length of time, which in this case is either 10 steps or 30 steps, you have to replicate it, right? So this is the input. This is the go signal. And as you can see, it replicates the pattern perfectly after 10 steps, after 30 steps. In fact, you can go to 100 steps and it will replicate it perfectly.
It isn't perfect.
Almost perfect, okay. Good enough for government work, right? Oh, sorry. No. Okay, it's really the comparison with the, you know, the random neural network. So here you see with at t equals 0, it's even having trouble with the pattern without having to have any delay period. It just gets washed out after 30 and after 10 and then 30, right? There's nothing left in this network. And it's been trained. Now the training, okay, let's look at the training. So here's the network trained at t equals 0, and here is the random network, and actually there's two different conditions, one with 100 units and 625, very slow. And this is traditionally with random RNNs, that's very slow training. Look at this beautiful traveling wave network. This is a log scale. And within 100 epochs, it's gone down by a factor of 100, and it continues to go down.
Why is it periodically?
Yeah, what are those sharp jumps?
That's not Andy.
You know, a lot.
Those jumps in the log.
You know,
Yeah, I think it's because the task is with these binary values and and on this log scale, if you make a very small error in the prediction of the memory, you're gonna get a huge spike in your gradient. So you can smooth that out with optimization.
But what you see though is after this jump, it keeps going down fast, right? So okay, this is dynamics of learning, right?
Is it the same slope?
Is what?
Is it the same slope? Can't tell. Each of
Yeah,
the-
this looks like the same slope. Yeah, you're
so
right.
7 different ways.
But here, this looks like the slope is even better. But in any case, this is it's even more dramatic here at t equals delay of 30. And then at and here, there basically is almost no learning going on. So what is this telling us? It's telling us that traveling waves are really good for holding on to information. In the early days of computers, they were called mercury delay lines. Literally, you press down the mercury and a wave would go down, a little drop, and you could read it out at the end, right? That's a memory. It's a physical memory, a physical wave, right? But this is even better because you could make these very large, and you can have information circulating, and you can actually compute with them, and that's what you're going to hear.
But sorry, Charlie. I must say the capacity is not necessarily so big because that memory is stored in the activations of the hidden units.
Yes.
Which is very small compared to the weight matrix, right? It's a small number of units. I mean.
Yeah, the order
so-
and units, right?
Yeah.
That's right. So that's right. This is an active dynamic memory. This is
Not
not.
a small capacity though, what I'm saying.
Oh, okay. No, well,
maybe
this is a tiny network, but the brain has 100 billion neurons. Okay, so just scale it up. Okay, we'll get there. Okay, now, this, now this
Should
is,
we be thinking about this as a readout?
What?
Network, a readout network?
hippocampus.
Should we be thinking about this
Oh,
as,
okay, readout. No, this is actually, one of the nice things is that it learns how to read out. You give it the go signal and it learns how to read out. You know, it turns out that there's a lot of manipulation you could train it to do. And you'll hear from Andy much more about that. Okay, now I'm gonna take you into the brain. So a few basic facts. I'm gonna build on what you heard from Michael. So one of the facts about the cortex that is in fact important for spatial context is the fact that if you're sitting here in the middle of a column, this is the strength of a connection between this neuron and neighboring neurons, right? And so this is a column here, that's a column. So you have a high connectivity locally, falls off, and in fact becomes inhibitory in the next column. And I'm oversimplifying it. But if you actually look at the weight matrix for a cortex this 1D cortex that has 60 units, presynaptic strength of the synapse with the postsynaptic neuron, this is what it looks like. Does that remind you of anything? It's a Topless matrix. Okay, this is called in machine learning inductive bias. In other words, if you know something about the problem you want to solve, and if you know that particular connectivity may be a much better one to start with, you start with it. And that's what happened over evolution. Nature came up with this connectivity pattern, perhaps in order to solve a problem in temporal context. Now, it has a long history. It's called the ring model. And if you analyze it mathematically, it turns out to be a line attractor. That is to say, if you look at the energy, the activity pattern, it's going to go down to a line, no matter where you start, and that's neutral along the line. In other words, there's no more motion unless you push it. But once you push it, it keeps going.
But it's a little bit confusing, Terry, I must say, because this is centers around or something here, basically. You know, the center is average and then it's around, so it's a spatial. So what you're showing there is a spatial high pass filter. Spatial high pass filter, not top temporal.
Yes, it's spatial.
That's
pattern.
true.
Yeah.
There's a lot of history here. I'm skipping over. Yeah, I mean, the Mexican hat is seen in ganglion cells. It's seen in LGN cells. It's seen, in simple cells. It becomes spatially organized.
Because Toby's saying this is not the temporal evolution. You can have a similar thing in time, and that's what the equation says.
Well, no, this is space. This is space.
Spatial, yeah.
This is space. This is space.
Right, a similar
But now you're right. Now the question is, what about time? Now what I'm going to show you now is this is my levels diagram. You've already seen it. John has introduced it, and it makes sense from the perspective of neuroscientists because what I typically do is, talking to students, I say, I want you to tell me where you are on this diagram. They'll tell me, well, I'm doing my thesis on networks, neural circuits, or I'm working on synapses, or I'm working on cortical maps, right? And you put yourself into that diagram, and then you can see, there's things below me I need to understand. There's things above me that it's going to illuminate. Okay, so this is a good way to organize a lot of research. But now what I'm going to show you is that there are traveling waves in the cortex at many different spatial scales.
And not at the molecular level?
Talk to
Masking, I don't know.
so actually, Kavanaugh can answer that question. He has a Nature paper, right? Where he uses ion channels in the dendrites to talk about interactions along the apical dendrite. So, okay. Yeah, the answer is yes. Why not?
Bacteria have some stuff like this, but I don't know if it's the same.
Well, bacteria have flagella that go like this.
You know
right?
what I mean? They do some way.
Oh, chemical. They also have chemical
Yeah,
oxidations.
I don't know if it has any.
No, there's a lot of chemical oscillations. There's cell cycles. Okay. So here is what got me into this business. So I was working on sleep and collaborating with a group at Mass General where they were doing recordings from the surface of the cortex in humans with epilepsy. And this is, the purpose is to isolate, and identify where the focus of the seizure is so that they can take it out and hopefully stop the seizures, right? That's the goal. But in the meantime, they're implanted with these electrodes for a couple of weeks, waiting for seizures. And just constantly, all during the day and night. So we analyzed the data, and this is Lyle Muller, who was a postdoc at the time. And so what are we seeing here? Okay, this the gray level tells you normalized amplitude of what's called the sleep spindle. So if you record EEG, what you see are these little blips that last 1 or 2 seconds and 10, 14 hertz. They occur thousands of times during the night, specifically in slow wave sleep. And here is, we filter it actually, I think, between like 5 hertz and 20 hertz. It's very noisy. But here you see the actual trajectory of that point. But now I'm going to play a movie. Let's hope it works. And I want you to tell me what you see in the pattern. Okay. Follow the white ball here. Okay. Frontal, temporal, parietal. I'm giving you a hint. It's a traveling wave. It's a circular traveling wave. It's global. Now, the concern is that these are epilepsy patients, maybe these are damaged cortices. So we teamed up with Abel Benesich and we high resolution EEG in babies who have a skull that is soft, and you get beautiful, beautiful sleep spindles with very high amplitude. And now you can actually see both hemispheres. It's traveling waves, and babies spend half their time sleeping. So this is great. We had tons of data. And that's an interesting story in itself. Okay, so we tried to model this, and we used the line model. This is the ring model. So we have a bunch of units, and we connect them up locally with excitatory connections, and then further away with this is a connection to an inhibitory unit. That's how it's done in the cortex, by the way. And then we also put in time delays. That's critical. There's axonal time delays, especially over long distance, right? You have tens of milliseconds of time delay between one part of the cortex and the next. Now, we tried to do was to come up with
The time delays is in the leads.
that, the further it was, the longer the time delay, right? We should assume that was like an axon, the velocity is a constant velocity. Yeah. Now, if you do this with a small network, you get what is called dense traveling waves. That's actually what happens in epilepsy, where all the units are being activated in sequence. That's not what you see in the cortex. What you see in the cortex is a very small fraction, very sparse. Typically a few percent of the neurons are spiking as it goes by. And we could not replicate that until we made a network that had 100,000 units in it. And then we got beautiful traveling waves. Here, I'm going to show you what they look like. Now just look at this. I mean, look at this. It's traveling. And they go through each other because it's very sparse. Look, isn't that beautiful? You have no idea how happy we were when we sat, right? This is a lesson here. Almost all the work in complex neuroscience is done with small networks, a few hundred or 2,000 units. And you need to scale it up to actually see something that is comparable to what you see in the brain. If you do a Fourier analysis, spatiotemporal, that slope is the velocity, power spectrum. By the way, these are integrated fire units, and they're spiking, right? And it falls off just like you see in the cortex. So this is like, this is a small model, brain standards, but it was a lesson. Okay. Now I'm going to ask the following question. And this is where the going gets rough, in the sense that I'm going to depart from a received wisdom in 20th century neuroscience. Yes, go ahead.
So the traveling waves are basically like a linear perturbation?
Yes, okay, that's a really good question. They have a constant velocity, yes, okay. You're
And,
absolutely
and
right.
they're linear in that they superimpose without.
They do,
without
they do,
distorting
they
each
do.
other.
So
Yeah.
that's a really good point. So what we're looking at here is perturbation from the firing rate.
Yeah.
Which is what everybody looks at when they are analyzing data. Yeah.
So I'm curious, do you see any difference in these different neural models of whether you need the problem size to get that big or not? Because certainly you can get a lot of interesting traveling with phenomena and related kind of dynamics versus anything.
We actually did look at a couple of different models. An earlier model, which I'm not showing you, is coupled oscillators with time delays in it. You get beautiful traveling waves there too. No, I think this is gonna work as long as you have with many different simple models, detailed models with Hodgkin, you know, this is a universe. Okay, now when we saw this, okay, everybody yawned. So what, right? So we went to the literature and we wrote a review paper in Nature Reviews of Neuroscience. There's more than 100 papers out there where people have seen traveling waves with, you know, arrays of electrodes in every part of the cortex, in every frequency band. Everything is called an oscillation. You know, when you put your single electrode in, you see an oscillation, a gamma oscillation, 40 hertz. That's a traveling wave. You're never going to see a traveling wave with one electrode, right? And so, you know, and so we go to our colleagues and say, well, you know, what do you think's going on here? So actually, they shook their head and said, well, we have no idea, right? I mean, I don't know, it's always there. In fact, one of my colleagues said it's the exhaust fumes of the brain, right? You know, it's ignored, is what it is, doesn't fit in. Here's the traditional view of the single neuron, is you give it a stimulus and after a little delay, you get a firing rate. And it's the rate, not the spikes timing, it's the increase in the firing rate. And that represents that stimulus at that time, when that neuron fired, right? Okay, what I'm going to tell you is that there's an alternative to that, to that interpretation. So let's just look at a traveling wave, a very simple one. Okay, this is a flash of light at a particular location. And we now know, this has been seen with optical recording, that after 20 milliseconds, it's a ring that expands, right? Now, you might think that by this point here, you've lost all the information about the stimulus, right? Because first of all, it's 40 milliseconds in the past, but actually it's all there. First of all, you take the center of the circle, that's where it started. You take the radius of the circle and it tells you how long it was since the stimulus. So the information has been recoded in the spatial temporal pattern, information about the past in these traveling waves.
Is that an impulse response of some sort?
Yes, it's an impulse response with this it's a single flash that stops here, and as you can see, it expands. Okay, now here's now the new conceptual framework, which we called cortical. No, I misspelled that. Cortical space-time neural representations. And here's the kind of the kernel. You have two neurons. And you get an input here at time t. And so this is what they see when you look at the receptive field of a cell in the visual cortex, say. But, you know, at a time delta t before that, B got an input and it fired. And then because of the time delay on the axon, long-range horizontal connections, they're unmyelinated, they're very slow. Now A is getting some information from B in the past, right? It's mixing things coming in now with things that have come in before. And the further away B is, are you okay? Okay. The further away B is, the longer the time delay. So here's the space-time diagram. So you have a bunch of inputs coming in. This is, you know, it gives you a sense for all the density of neurons in the cortex, and then not all of them are getting activated because, you know, we know it's a sparse activity. But the point is, though, that because of the fact that there's a velocity for these long-range horizontal connections, everything within blue here can affect the spike on this neuron at different time delays. And the further away you go, the longer the time delay. And that means there's a window of this neuron is actually seeing information from a window of time. Right? And there's hundreds of milliseconds in the cortex. These long-range horizontal connections go for many millimeters, 5-10 millimeters. Now, here's the new picture. And I should tell you that you can prove a theorem that if the traveling wave is linear, which is a good assumption, that all the information that came in can be extracted from it, from a regression. So you haven't lost any information, you just recoded it. In other words, if you look at all the neurons at this time t, you can reproduce the inputs that occurred at all the times in the past. Yes.
How robust is this to like jitter?
Well, it's interesting, okay? And up until recently, neuroscientists always thought that, well, if it's firing rate, then it doesn't matter what the jitter is, because it's only, you're averaging over 100 milliseconds, right? So something like that. But actually, Zach Maiden and I did an experiment where we actually injected noise and showed that the spike timing was precise within a millisecond. And what that means is that the neuron, the spike initiation, is exquisitely sensitive to the fluctuations coming in, right? So, so the machinery is there, but and now we actually make a prediction. Okay, people, what they typically do when they do a reconstruction, they get their population and they try to then predict what the sensory input was at that some moment in time. What we're saying is that you should be able to get the input that came in, reconstruct the input that came in earlier in time, right? If what I say is true, there's information there about the past. So now we're talking about encoding an interval of time, activity that has occurred over time, right? And the traveling wave is particularly good, as you just saw from the RNN model, to holding on to information for a long time. And so here's what's happening if you have a bunch of inputs coming in at different times, 1, 2, 3, you get an interference pattern. That should remind you of something. Do you know, have anybody seen the hologram?
I know all about holograms. This was making me think of Carafect fiber memories from back in the day when they couldn't. So basically in optics, you can't make memories very easily.
Ah.
So they would do loops instead.
Oh, really?
They would have the memory travel around until they were ready to release it. It was one of the things that they,
Okay.
instead of having to go through an electronic step. But I also know a lot about holograms, yes.
But this is a very special kind of a hologram because it's not, the hologram is spatial.
Yeah.
Spatial. This is space-time. And this is a completely different conceptual framework. And it's I tried to, many times to try to get my colleagues to switch. And I get them to switch for about 5 minutes and then they just they go back, they regress because.
So it's like the reference beam is the brain itself and the object beam is the information coming in. So that you can sort of
That's right.
essentially,
Yeah.
you know,
you have the interference is a reference beam with the reflection from the object.
So, Sherry,
Yes.
you may say it at some, how far apart do these have to be so that you can keep them separate? Because in the brain, it's gonna be going on through time.
Right.
And one of the problems we always had trying to figure out what to do about it was how to keep segments that it seems like you want to keep from interfering with each other.
Well, in this case here, you
Or
want them to
actually in
interfere.
a forward way, because it's all,
So
time
this
is
is, so you are my prototype. You see what I just told you, prototypical neuroscientist. This is a whole new way of thinking about it, and you can't use your old way of thinking about what's going on with firing rate. You're thinking.
No, I wasn't.
You were thinking just about the traveling waves.
Yeah.
No, it's if you saw it. I mean, the traveling waves can go through each other.
Yeah.
By the way, there's two different kinds. This traveling wave is stimulus driven, but there's also spontaneous traveling waves. We'll talk about that later. Yes.
Okay, one comment, one question. Programs rely on brain mechanics. Here we have classical mechanics. I mean, the brain is a classical machine.
I'm not saying this is quantum mechanics.
No, wait a minute, I mean, I'm just.
No, but what they do say, they have a similarity, maybe there's waves in both, right?
So.
So maybe, nature has,
Maybe.
reused something.
So.
By the way, this is, for physicists, this is, space-time is, is the kernel of relativity. All information is transmitted in physics with traveling waves, electromagnetic waves, sound waves, gravitational waves, right? That's how you transmit information in physics.
You got the pedals on, you got your pulse, like, your patterns of waves, but it's still physical medium.
Okay, well, I have to move forward. Okay, so this is from Mark Schnitzer at Stanford, optical recording on the surface of mouse B1. And what you can see here is that this, for example, at the top, there's two different trials, event one. And I think this is spontaneous, but in any case, it starts here and it goes across. Here is the trough, it goes across. And then at different locations, you can see there's a phase difference. It's all about phase difference. In other words, it's relative timing. That's important. It's not the absolute time. It's the relative time between two locations and with the phase differences between them. That's what encodes the information. It's a phase kind of
So,
encoding. Yeah.
so like in Schnitzer's data, is that calcium imaging or is that?
No, this is voltage sensitive dye. He has tweaked voltage sensitive dye, so he gets very high sensitivity. Funded by the NIH.
One of my projects.
There you go. No, I'm on his one of the advisory panels, and so I saw all of this and I said, wow. And this is, by the way, gamma frequency.
What's the amplitude of the voltage modulation?
It's that's a great question. I have his slide, so I can answer it, but not right now. Okay, hippocampus. The mother of all oscillations is the theta oscillation, 4 to 8 hertz. And it's just beautiful. It's huge. It's like a millivolt local field potential. And it's only when the rat is exploring the environment. When it stops, it disappears, right? So Thanasiopoulos in 2008 put an array of electrodes in. And here's what he saw. He saw these beautiful traveling waves, right? So these are lines of electrodes. And so you can see that it's traveling dorsal to ventral. And here's a movie. Seeing is believing, right? Just like before, it's coded. Dorsal. Uh-oh. Trouble.
That's medium, not fast.
Okay, so there's a glitch here, but it actually does travel like this, and it's 1/2 wavelength across, and it just travels. The peak travels across. Now, I have colleagues who study hippocampus, and I would on the thesis committees, and I would always ask at the end, they were doing place fields and classical stuff. What about these traveling waves? They're there in the background. You know what the answer is? That's not my problem. Okay. Hippocampal replay. I'm gonna actually jump.
No, Henry, I mean, as neuromorphic engineers, we look for a function for this. So is it to really link or bind things over long distance?
It is. It's over long distance in the cortex. That's I think exactly what I think is that's a way to connect information in different parts of the cortex so that it's phase encoded in terms of the spiking. Okay. So look, we have a paper that just came out, Neuron, a couple weeks ago. I went through it, I think, last year, but just to give you a sense for what we did, if you look at the hippocampus, there's a trisynaptic arc that goes from the entorhinal cortex superficial layer to CA3, which is a highly recurrent network, to CA1, which is the output that projects back to the lower layers. And you saw this all in Monday's lecture. This is basically entorhinal cortex is kind of the last step in the hierarchy of all the sensory input that's going into it. So what we did was to have a very simple model, which is a model which goes way back called an autoencoder. The autoencoder takes in an input, a layer of hiddenness, and an output, and what you try to do is through a bottleneck, try to learn to reproduce the input. That's an autoencoder. What we did here was do a predictive autoencoder because we wanted to learn a sequence. And instead of a layer of hiddenness, we have a recurrent neural network. And you can train it with backprop through time. You get, it's a different loss function. If you're interested in the details, you should go and see it. Now, one of the things we did, CA1 has this, we know there are place fields there. They appear literally within less than a minute when the rat goes to an environment. One-shot learning. Well, in our model, CA1 is the comparator between the prediction of the next input coming in from the entorhinal cortex. And you see CA1 also gets another input from CA1, a direct one, so there's no delay. So you can compare the prediction of the next input that is coming in, and you can compare the two, you subtract the two, so it's an error signal. It's an error signal, and of course, it's going to be there immediately because the recurrent network hasn't learned yet how to predict. But over time, it turns out, and this is also Mark Snitzer, if you normally what people do is they look at it, they do an experiment, they come back, they have another rat, do another experiment. But if you do it over a month, it fades away, right? And it also, it turns out, it fades away in our model. Why? Because as it learns, it gets better and better, and then the CA1 response to the model disappears, right? So that, and we can put more than one input into it. Now here's the part that connects to what I've been telling you, okay? So, okay, what are these neural networks, they're called black boxes, right? Why is it? It's because you don't look in it, right? But you can, you have access to every single activity of every unit, and you know every weight, you know every input. Come on, you know? It's your fault if you can't figure it out, right? It's there. You should be able to, unlike the brain where we have a real tough time, we can't record from everything at the same time. But here's what Yossi Chen, who actually did this for her thesis, showed was that in actually two environments, this is the weight matrix. And as you can see, it's the Mexican hat.
Kind of, yeah, it's a very noisy Mexican hat.
It's sparse. That's the exact point I want to make, is that you can get, it learned to use traveling ways to solve this problem using this kind of a record of a sparse connectivity, which is excitatory to, by the way, in the hippocampus, it's not topographically organized. So we reordered these units actually, which you'd have to do in the hippocampus to be able to see this kind of connectivity.
And the sparsity is like half or.
No, I can't tell you the exact number, but we store two different sequences, and we went through it. Actually, we actually learned MNIST digits sequence, and then we also did these sprites that do this and have different clothes on and so forth. No, it actually, you can store a lot of sequences. Yes.
So did it learn this Mexican hat to solve some problem? And then I would wonder which.
Yeah, that's right.
Did it just learn kind of contingencies in the environment, like proximity relationships?
Well, no, in this case here, we trained it on a sequence of MNIST inputs, handwritten digits. And it had to, we gave it, and then after learning, you give it the first one, you give it a 0, and then it spits out 1, 2, 3, 4, 5. And we know the hippocampus can replay at night to the cortex. So this is a model of replay, right? And we actually had 2 different sequences. So and it had to learn both, right? So that's.
Still not running in the environment anymore.
We actually did. We did have it run in an environment. We created an environment. It actually created place fields. So go to the paper. We basically went through. And by the way, it was tough getting it through the reviewers because they did not like this at all. Hippocampal people don't like being told that what they thought was a place field is an error signal. They don't like this.
So, Harry, so to we conclude, Kevin, should we conclude that if you want to learn sequences, you're gonna.
You should start with the triplet matrix.
Yeah, so that's really about.
That's the
learning
bottom line here, is that, we can discover this through brute force, or you could put it in from the start, and that's what Andy is doing, right?
But there is just proximity, it's just the neighborhood relationship, right? The Stochastic matrix is just the neighborhood relationship. So there's a neighbor, on the left and the right, and then the further neighbor. the further neighbor.
But what's wrong with that?
So that's a natural, like a very natural prior for some tasks where you have these proximity relationships, and for some others, we not.
Okay, I'm really, this is, I don't have enough time to go into detail, but come to Andy's section tonight. He can give you answers to all of these questions, okay? But I've got to go on because I have a little bit more to do. Okay, self-attention. How is that done, right? So I told you that the way that the transformer works is a big loop, right? The decoder is spitting out one word after the next. Okay, I'm talking to you. I'm spitting out one word after the next, right? And we know the basal ganglia is really essential for that. The basal ganglia is procedural learning. It allows you to memorize sequences of actions, right? Playing tennis, talking, So here it is. Here's the basal ganglia, and this is in Michael's talk. Here's the cortex. It's topographically mapped onto the basal ganglia. This is the equivalent, the putamen striatum input layer. And then it goes to the thalamus through a couple of other places. You don't have to know the details. This is actually for the motor cortex. It's topographically organized in the different parts of the basal ganglia. But then it goes back. It projects back, and it loops. And this is the loop that gives you sequences of actions, right? So it may be that and now remember what I told you about the multi-headed attention, is that it actually is something that's done in parallel with the information coming in to the cortex, and this is combining now. The cortex is combining information coming from sensory input and from this path through the basal ganglia, and so this is very speculative, but maybe there's something like a self-attention signal in the basal ganglia. And it turns out that went to the literature, again, these papers are completely ignored. There are traveling waves in the basal ganglia, So it's traveling waves all the way down. So I mean, so here's the hierarchy in the cortex, V1, V2, V3. And then here, everything projects down to the basal ganglia and then back to the cortex, and each one has each layer, just like this is one module of many. You have a stack at 100 high. No, this is all speculative, but it makes predictions, tells you that maybe there's within basal ganglia, the relationships between inputs from, by the way, this is not purely topographic like the LGN. This is it's broader in terms of the activity that converges on a single unit. It actually could come from more than one area. Right? And we know that you can learn. This is, the neurons, dopamine neurons are reward prediction error, right? And by the way, reward prediction error is exactly the same. You learn to predict future rewards, right? Just like the transformer learns to predict the next word. And it turns out the cerebellum learns to predict the next sensory input, right? That's how you train up a forward model. I think this is the kernel of how nature is able to solve all these problems. Okay, so here are the predictions. Waves of the cortex, hippocampus, and temporal context. And by the way, when you get to as you go up the hierarchy, the window gets bigger and bigger, and prefrontal cortex, you know this from fMRI, becomes seconds and minutes, right? So that's where the integration is probably occurring across all those saccades and all those, video clips. Connectivity matrix is a line attractor. This is a big one because it will happen. Well, connectonics will actually work this out for us. It's not obvious because there is no topographic organization in the hippocampus. Primary function of CA1 is to represent prediction error, to learn sequences. One-shot learning is one-shot error. the cortex and the basal ganglia implement a transformer. I mean, these are all testable things. So finally, okay, the last question.
To the point, could we come back to this point with million tokens that need to be stored in transformer to work? That probably are not stored in humans.
Yeah, so now let's just think about this, okay? So the encoding part, what I told you, the encoding part of the transformer, right? But now what about the decoding part, right? That's a motor system. That's why the basal ganglia is involved. And now here's the mystery. What the heck are these spontaneous waves doing? I think spontaneous waves are basically refreshing your space-time code, so that you can constantly encode information from the past that will last for many seconds and minutes, right? So I think that this is how what actually the psychologists call long-term working memory. This is different from what neuroscientists study when they give a monkey a task to remember where the spot of light was a second ago, and then when the spot goes off, the monkey has to remember and move its eye. That's short-term working memory, and this is maybe it's using the same mechanisms. We know that there are neurons that actually maintain firing during the delay period, so maybe that's a different solution to short-term working memory. This is a solution to long-term working.
But it's not in terms of words, right? Like even with the rehearsal, I don't think that they remember 20 words from the last sentence.
This is not rehearsal. This is not rehearsal. This is happening subconsciously. It's
rehearsal in this way, but it doesn't happen in the world of words.
It's what?
It's not in terms of the words tokens that they store.
Oh, no. Okay, okay. Look, the machine learning people have found a solution that is matched to their hardware, what their hardware could do. Nature had to work with constraints of the hardware that nature evolved, right? And now you're going to see tonight that you can do a lot of computing with traveling waves. It's not just holding on to information. You can actually get things. You can do variables assignment, for example. It's a computational engine. And that's the message. The message is this is very powerful inductive bias that we know the brain has adopted. And now the question is to explore that. And by the way, I was inspired by Christopher Reeve's talk, right? He said, "Oh my God, state space models." Well, that's the brain. The brain is a state space model, very complex state space model.
Yeah, so you talk a lot about Topos matrices, but that's a special case of a class of matrices in which the upper diagonals are zeros past some level. And there's a Hankel matrix, which is the whole upper triangle. And those don't produce traveling waves, but they're representations for sort of causal behaviors.
Oh,
so right, have you guys seen those showing up anywhere?
Actually, the Andes matrix is like a causal. It's not.
It's zeros above some super diagonal.
Yeah, or there's a variety of different things. Most of the stuff that I've worked with is like finite difference approximation with some differential.
Oh, that's how they want to do. Yeah.
Okay.
I'll save this for tonight. I'll save it for tonight.
So
there's a whole family of things like that.
So I just want to let everybody know, you'll see now is up at University of Washington. Lyle is at Western University in Canada. Andy Keller is right here. And Max Welling, he's delocalized, because he keeps popping up all over the place. I think he's at Caltech right now.
He's a Caltech, right?
Yeah, okay.
So, question?
Yes.
So have you actually done explicit decoding in kind of networks with these traveling waves to
No.
to decode the identity of the stimulus several time steps in the past?
I haven't.
Yeah.
But I think when people are set up, they could do this experiment tomorrow, because there's by the way, this idea of.
I'm asking, have you done that in your network models?
Oh, in the network model. Well, I think that yeah. And that one little network I showed you basically is reconstructing the past, right? You give it an input, and then you give it a go signal, and you reconstruct it, right? Something that happened a long time ago.
Mm-hmm.
Yeah, and it's really
but your framework is kind of this superposition of traveling waves is
right.
is actually representing, a set of stimuli going some distance into the past, so.
Yeah, okay, okay, but
That
remember
suggests
the,
that at every moment, you could look at activity and
yes.
code with some accuracy what the stimulus was. in the
Okay,
past.
okay, so remember what you gave it a sequence of binary inputs, right? Over time.
Yeah.
So that's a window of time, and somehow those got encoded into this traveling wave that was, I mean, and we know the information was there because we can extract it at the end, and now you're asking if halfway through we look at it, what does it look like? And Andy, have you ever tried looking at that?
Halfway through.
Yeah.
I'll show you videos of the hidden state over time. You can effectively just kind of see it propagating around. It'll make sense when like you look at the equations. You can think of like a shift register, like a queue. You're pushing items onto the stack and that kind of rotates around. So you can definitely decode infinity like that.
Yeah.
Okay, but the thing is, so what I'm trying to get at is like, is this like a general short-term memory? So like.
It's like a delay line.
Yeah.
Things.
But actually, there's a really nice paper. I think Surya Ganguly was one of the co-authors. Which is beautiful, and what it showed is that you can analyze recurrent neural networks before transformers or anything. And what you can show is that you can do push and pops. Right? The finite state of time, you can push and pop, and that gives you a lot of computational power if you can do that. You can show that it actually is the most efficient way of doing it with the memory in terms of the number of units and number of parameters. So recurrent networks actually are very, very over time.
5 o'clock math. If anybody's ever seen. There.
That should work. Okay, I'm actually gonna give kind of two talks because they're connected. One is, this is based on a paper that I published recently, basically arguing for two parallel hierarchies in speech motor control. Okay? And then that turns out that has some implications for this, the idea that speech coordination is that speech is the basis for our ability to move to a rhythm, essentially dance. Okay, so that's the argument that I'm going to do, but I want to give you enough background on that. That speech is actually, so speech coordination, the need to coordinate speech is the basis of our ability to dance. What's that? It could be any number of things, but I'm gonna argue for this position.
What about nonsense, bears and monkeys?
They can't do it. We'll talk about it. Yeah.
No, I was like to say something in agreement with you, otherwise all the other animals would have been.
Yeah. Yeah, we'll talk about that, but I want to give you the speech background first. So you're familiar with Broca. Broca was very interested in the faculty of what he called the faculty that coordinates the proper movement of articulated language. That's what he thought he was localizing. We know now that Broca's area, which is this region here, is not doing that. Okay, we don't know what it's doing exactly, but it's not that. So people have argued that it's anything from cognitive control to word selection, syntax sequencing, not clear, but it's not doing relatively low-level speech coordination. So then the question is, where is that system? This was what I was interested in looking at. And I'm going to argue that there are two. Both are on the precentral gyrus. Are we pretty familiar with neuroanatomy? No? Okay, I'll show you where this is. One is posterior to Broca's area. The other one is a bit more dorsal. So on Broca's, this is Broca's original case. That's the brain survived. We have this original case. You can see the damage in Broca's area. These are the regions that are important for coordinating speech. The actual lesion, they scanned this brain. The lesion is huge and it extends all the way down. But that's just a historical note. Okay, so I'm going to talk about some of this evidence for the existence of two speech-related areas. That's the first point that I'm going to make. We've seen this in functional imaging since the 1990s when people started doing this. And basically, these are speech tasks where people are listening to speech and also producing speech in various ways. So these are areas that respond both to listening and to various kinds of speech production. And you can see these two areas. In each case, this is from some of my own studies. Here you only see the dorsal one in this particular study, but the dorsal one was the interesting one because when we were doing this work, trying to map speech circuits and language circuits in the brain, we would see things like in posterior regions, which is kind of Wernicke's area, the other main speech or language related area, it has been thought. And then we would see something that was close to Broca's area, and then we saw this other one. So as a field, we completely ignored this more dorsal one. This is the precentral gyrus here. These are those two locations that I'm talking about, okay? No one really knew what it was doing, but we knew that it was consistent enough that in neural architecture models of the organization of language and speech in the brain, this is from the paper that I wrote with David Popple in 2007, basically arguing for a couple of streams of processing speech, a ventral stream for comprehension, a dorsal stream for sensory motor integration and speech production. I drew it in, this more dorsal one, because it kept showing up. But again, we never knew what it was doing. So that's one bit of evidence. There are two, and I'm not going to go over all the evidence. There's more evidence available, but I'm going to give you the highlights enough to get us to a basic understanding.
That picture before you had comprehension of both sides, but production of only.
Yes. Yeah, that's right. So one of the things you talked about, Malcolm mentioned sensory motor integration, and yes, it's true that the motor system does activate when people listen to speech and comprehend speech. Turns out that it's not necessary for comprehension. All you need is the temporal lobe and it's mapping onto concepts. You can take this system completely out and people can comprehend speech quite well. Okay, so that the motor system is not necessary for perception. We can talk about that. I wrote a book about that. There's a whole bunch of stuff. It's not like everyone thinks that the motor system is important for perception. It's important for production. And it's more like it,
Yes, this, but suppose it's important for learning to speak.
yeah, well, so all these experiments have been done. So no, it turns out you can
suppose. So you test against.
Oh, you find people who have cerebral palsy and have never learned to speak. Do they comprehend speech the other way? Yes. You find people with bilateral lesions in these areas called the percular syndrome. Never spoke in their life. They can comprehend speech fine. So you don't need it developmentally. And then there are the animal experiments. Japanese quail and chinchillas can perceive speech quite well, show categorical perception, all the usual things that we see, and they don't have the genetic capacity for speech. So that's how you test that sort of thing. So anyway, yeah, so that's the story. The perceptual system, the comprehension system is more bilaterally organized. The production system is more Nash dominant. Okay, there is a syndrome, a clinical syndrome that corresponds to difficulties in coordinating speech. It's called apraxia of speech. It's defined literally as a speech coordination deficit. It's not a low-level motor problem. They don't have paralysis or weakness in their speech articulators, but they make a lot of planning errors. It's how people often talk about it. Make a lot of speech errors in their production. The regions that are implicated, turns out not Broca's area. This is Broca's area circled. These are left hemispheres, left slices, even though it's rotated, that's typical radiological convention. So Broca's area, so let me tell you what this is. These are acute stroke patients who have been diagnosed with apraxia of speech in the ER, and these are scans of essentially blood flow perfusion that shows, yeah.
What is apraxia?
Apraxia is a motor disorder. So apraxia, you can have limb apraxia, where you can't coordinate your arm, say, normally, things like that. So like if I asked you to do something like this and you had apraxia, limb apraxia, you might do something like this.
So these people trying to articulate speech and they have some motor issues.
Yeah, so it sounds kind of like, just to give an example, trying to name a picture of a cookie jar. They might say it's kind of like that. But then they'll be like, I know what it is. I just can't say it. I don't know why I can't get it out. So they're fluent, in general. It's not a motor
So,
problem,
I
but
had
it's a
a
higher
friend
level
who had a
planning.
stroke, but he could sing.
Yeah,
Yeah.
okay, well, bring that up when we talk about these two circuits, because one of the arguments is that dorsal one is related to song. Different from the articulatory. Okay,
The example you gave of the arm,
yeah,
look, or sounded like it's at quite low level. Whereas the articulatory was quite high level. So why?
it's
are
kind of,
they-
they're both,
Strokes are in the same place nearby?
no, they're different, for the two types of, they dissociate. Limbipraxia and speech apraxia.
Apraxia can be quite low level, but it can also be.
It's an inner, I think of it as an intermediate, it's not a high level kind of planning system, it's more like the example that I articulated. It seems low level, like you're not quite stuttering, but you're having problems getting into sounds. A lower level dysarthria would be more like, you know, putting a pencil in your mouth and trying to talk. It's constant, you can't form the words. And this example, you know, you can have examples of limbipraxia where you say, show me how you would salute. And the person is like, they just can't quite coordinate it. But then you know, if you give them a task to do, they might scratch their eyebrow or something and do the action. So it's not a low level articulatory thing, it's an intermediate planning thing. So these are the regions that are implicated in apraxia of speech. I want to draw your attention to the fact that Broca's area isn't involved extensively, but you do see a lot of involvement of the precentral gyrus, both ventrally and dorsally. So there's lots of controversy about the neuroanatomy of this syndrome, but the point I want to make is that it involves both of these areas, okay, as well as other areas. That's all right. So what are these two regions doing? And so that's what I set myself to figure out. So here's the claim. The dorsal, but not the ventral one, is involved in controlling voice pitch during speaking and singing. It's that aspect of speech. The ventral, and it codes pitch-related acoustic features during listening. So actually, I'll show you evidence that it actually looks like primary auditory cortex, oddly enough, in terms of its spectrotemporal receptive field properties, its acoustic sensitivity. The ventral one is more involved in coordinating phonetic level planning. So like control, and so you can think of it as the dorsal one is controlling your larynx, which is mostly where your pitch control is. The ventral one is controlling your supralaryngeal articulation to form phonemes and syllables and stuff like that. So let me show you the evidence, at least part of the evidence. The major source of evidence, here we go, is a study by Eddie Chang's group, where they had people reading sentences where they put a pitch accent on different words. So like, I never said she stole my money. I never said she stole my money. I never said she stole my money, and so on. And what they did is they had a bunch of electrodes recording directly from the brain, and they asked the question, are there any areas in the brain that correlate with the ability to put a pitch accent on a word? Basically looking at pitch height, okay? And they found a region. So this is actually an intracranial trace, gamma power, and you can see that it's ramped up when you put pitch accent here. Pitch accent is here, here. So basically, that signal is correlating, increasing activity as a function of pitch height during vocalization. Okay.
Sorry. Are you claiming that this is a motor thing or?
It is motor related.
It could be an artifact of just the pitch response or something like that. It doesn't have to be motor.
It doesn't have to be motor, but it is correlated with pitch control. It could be purely auditory. Yeah, sure. You stimulate this area now. What part of this paper also was, if you stimulate this, so here's the area in their paper that they identified. It is both left and right hemisphere. It's not particularly strongly left dominant like other aspects of speech. This one actually shows a right hemisphere region. Okay. When you stimulate that area, you get vocalization. Or you can get vocalization. So people will phonate vowels, kind of like that. You don't get that when you stimulate down here. So it does have a motor function. Also, the same group identified the case of a patient who had, was it a stroke? No, I think it was a resection. They took out parts of the brain and the person ended up with chronic apraxia of speech. So there's evidence that it is doing motor related stuff, but it is absolutely true that this same area, and I'll show you this in a second, responds to speech acoustically.
They also look at just having people listen to these.
Yes, I think I have it in here actually. So here's speaking for it. So this is speaking, the trace in this area during speaking. You can see that it comes on and stays sustained. If you play back their speech, you get a response in that area as well. So well, we knew this from fMRI from years ago. The experiments that I used to do or still do, have people listening to speech, then they silently imagine saying it. And we get activity in the same area. It's that dorsal one that I showed you. Same area, both on the left, both listening and imagine saying speech. So this is no surprise here in terms of the fact that you get it for both. To figure out whether it's really auditory or motor, you can't just look at activity correlations. That doesn't tell you what's going on. You have to look at other sources like stimulation disruption, strokes, those sorts of things to figure it out. Okay. This is during singing, so they had the same patient singing, and you see this is correlated activity between speaking and singing in terms of the activity, pitch-related activity in that area. Okay, so it's singing as well. All right, so that's that. There's a little bit more evidence, so I'm not going to talk about it. That's enough for now. This is the study that was done in as part of my group. A former student of mine, John Venezia, was interested in mapping spectrotemporal receptive fields in auditory cortex. And he came up with a method called a bubbles method. So basically what you do is you take speech, you do it with 2D Fourier transform, and you poke holes in that spectral map, and then use that as a filter to reconstruct the waveform, now missing parts of the spectrotemporal signal. And then you look to see which areas respond to energy in different portions of the spectrotemporal map. Okay, that's basically the idea. And you can generate a map of spectrotemporal receptive fields. That's essentially how it is. You found all of these colored areas are regions where you can statistically generate a reliable map of some sort. Doesn't mean it's auditory per se, but you can get it.
So you're playing back the speech with holes in it?
Yeah.
And then you look to see which parts of the brain respond during the holes.
You correlate energy in a particular area with neural activity. So if you have energy in low spectral, low temporal modulation parts of the STRF, you'll find activity in certain areas that are sensitive to that. When that part of the signal is filtered out, a region that has that as part of its receptive field won't respond as strongly. So you basically do a bunch of these bubble reconstructions, so you're taking out different parts of the spectrotemporal modulation representation or information, and then looking to see what parts of the brain correlate with which. I'll show you a picture, it might make more sense. The interesting thing here is we see, not surprisingly, that you can map STRFs in auditory cortex. You can identify different STRFs, features that it's responding to, but we see this reliable region in the dorsal pre-central gyrus. This is the same zone that's implicated in these other things. It shows an STRF, looks like this. So these are the STRF maps, the map for this one. So this is in modulation space, low spectral and temporal modulation. This region here is the speech region. If you just have this energy in a speech waveform, you can understand speech. If you take that out, it becomes unintelligible. Okay, so that's the most important region, low region of the STRF. This region is more related to pitch perception. And what I want to show you here is that you're getting pretty broad tuning in this area. And this kind of map looks a lot like what we see in A1. You get tuning, different subregions will tune to different portions of this space. So this looks like an A1 typical kind of average STRF. Okay. And so that's the point. This is responding to pitch more broadly. This region here, which is part of Broca's area, doesn't show this pitch sensitivity. It just shows sensitivity to lower spectral and temporal modulation rates. Okay, is that clear? The main point here is that this looks like an auditory area. Okay. And it's sensitive to pitch. Okay. So
Broca's is also
It's missing the pitch from a sensory point of view, from an auditory point of view.
Yeah, so this is probably a higher level language thing. So if you have an area that is not doing auditory per se, but it's comprehending speech, then it will be active during speech comprehension and not active when it's unintelligible. That has nothing to do with auditory. But it'll look, if you do a map, it'll show up looking like this. So I don't think this is an auditory response. I think this one is because it's responding to lower level acoustic features. Moreover, this map only shows up when you're when the speech is when the speech is intelligible. When the speech is unintelligible or intelligible either, you can see sensitivity to acoustic features. I think I said that correctly. Okay, so I've told you that there are these two areas in premotor cortex. They're doing different things. I've suggested that the dorsal one is related to pitch. Okay, it's not just a pitch area. It is a region that's doing some kind of coordination, this kind of intermediate level planning, not low level motor planning, not super high level stuff. It's kind of this intermediate coordination kind of function. That's this area here. So what I'm showing you here is the location of what I started calling the dorsal precentral speech area. This is the ventral precentral speech area, that more ventral one, in relation to other bits of maps that we know about in terms of the brain. So the color codes are cytoarchitectonic maps based on other data. This green zone is premotor cortex, so we know that it's kind of making sense. It's intermediate premotor cortex, not prefrontal, not low level M1. This is a map which I'll talk about in a second related to dorsal laryngeomotor cortex. So that is low level laryngeal control. And then there's this other area called area 55B. So this is just showing the relationship that has interesting properties, and I'll talk about that in a second. The point here is that this is not an island doing something. It's part of its own hierarchy of planning. Okay, that's the argument. On the ventral side, people are really used to thinking about a hierarchy of speech control, from like linguistic-y things to low-level apraxia of speech-related things to even lower level M1 lower facial motor cortex. So this is the familiar hierarchy. What I've argued is that there's a new hierarchy, a separable hierarchy related to pitch control. That's the anatomical research here. So let me talk about area 55B first. This came out of Human Connectome Project cortical parcellations from Glasser Van Essen's group. They basically used functional activation, myelin maps, and functional connectivity to identify cortical parcels that kind of correlated in these different dimensions. The poster child in there, so they have a map of the whole brain, all of cortex, I should say. But they used as their example this area 55B because it was really clean. So here is the location of 55B. This is a myelin map, and you can see that it's the warmer colors are high myelin density. The cooler colors are low myelin. 55B is relatively unmyelinated in between two eye fields, which is interesting later. And it's just anterior to primary motor cortex, which is more highly myelinated. It also shows pretty focal activation in one of their functional activation tasks. This is story listening, so speech, listening to sentences, stories, and you see that activity. So that's interesting. Essentially, they argue that it's a language area in this area, in this region, and this overlaps. We've done the correlation analysis, aligning the maps, and this is 55B. The dorsal precentral speech area is the posterior part of 55B. So this suggests a further parcellation of 55B. Okay. Another interesting thing, if you do a simple meta-analysis like on neurosynth, if you're familiar with that, you can basically do an automated meta-analysis of all the functional MRI studies that would have coordinates reported on the term syntax. And if I can tell you how this works if you're interested, but just take my word for it. These are areas that are correlated with syntactic processing, loosely defined. Okay? You get the usual suspects, parts of Broca's area, parts of Wernicke's area. That's what you expect based on everything we've ever done. But you get this other area, which is the anterior part of area 55B. That doesn't mean that it's syntax. I think it's actually related to phrasal level prosody, which is related to pitch. Okay. But that's an interesting observation. So there is something languagey in this area suggesting a hierarchy. Suggesting a hierarchy, which is what I'm arguing for, okay? So this intermediate area, something higher level out here. Questions so far? So good, okay. So we looked at functional connectivity too. These are the dorsal and ventral precentral speech areas. We put a seed in there in two separate functional MRI data sets. This is resting state. This is a task. This is actually from Venetia's speech listening study where we mapped auditory receptive fields and looked at regions that correlated with these two zones preferentially. So the red ones are regions that are more strongly correlated to the ventral. The dorsal, the blue is more strongly correlated with the dorsal area. And what I want to point out is that the dorsal area is more strongly connected to auditory cortex. The ventral one is more strongly connected to high-level somatosensory cortex. Okay, so different functional connectivity profiles, particularly where this one is implicating auditory. Okay, so all of this has led to the dual coordination model. This is the paper that I started talking about. Here you can see the two hierarchies in frontal cortex, going from low level to higher level. I think this is, I forget if I put slides in for this, but I'll tell you about it. This region here is referred to as dorsal laryngeal motor cortex. Turns out humans actually have two motor cortices for laryngeal control. The one is homologous, the ventral one, it's down in this region here. The ventral one is also found in non-human primates. They have the ventral one, they do not have the dorsal one. So one idea which I think is correct is that in our evolutionary history, we evolved, one of the differences between us and non-human primates is we have voluntary control of our larynx. Non-human primates do not. So the idea is that this is the region that evolved connections to the brainstem nucleus that controls the larynx directly.
We see that primates can control the articulatory apparatus as well as we do.
No, I'm the opposite. They, non-human primates have reasonable control over their mouth and tongue and lips.
That's what I was saying.
Yeah, they can do stuff like that. But they don't have voluntary control of their larynx. So they can make vocalizations, obviously, they're innate. But to try to train them to go, you can't, they won't do that. Birds can, yes. Songbirds.
Some animals that are like
Yeah,
different
right,
from us.
right.
They have great control of their.
Yeah, absolutely. So they're vocal learners like us.
So you are saying this is more than just pitch, really vocal learning.
Well, it is one component of vocal learning. It's the laryngeal component of vocal learning. The song really
do well with the articulatory learning.
do what do well?
To learn articulatory,
Yes.
are they as good as we are?
They meaning who?
Monkeys.
Monkeys. No, we're not quite as good at articulatory control. We're really good at it. But they do have some voluntary control. You know, like they grasp things with their lips, they can manipulate food, things like that.
Maybe you said it already, but is there any evidence for the dorsal larynx part in non-private, in non-human primates?
Any evidence for?
Have people looked for the second part in non-humans?
Yes, they have.
No.
Yeah, no, there's no vocal, no control there. There's no anatomically, there's no direct innervation from no direct connection between cortex and the brainstem nuclei that control the larynx. Whereas we seem to have it.
And in humans, those two areas project the same circuit or different?
These two areas at the level of cortex, like I showed you, the inputs are different. In terms of the descending pathways, it's really hard. Unfortunately, the nucleus that controls the larynx in the brainstem in humans is called the nucleus ambiguous. And it's called that for a reason, because it's really hard to sort out the connectivity. So really a detailed anatomical study in humans for ethical reasons as well as the ambiguous reasons is hard to do. So it's assumed there is some evidence. I consider it pretty weak concerning direct connections, anatomical connections, but functionally it's got to be the case. So that's, and that doesn't exist in non-human primates.
Where do you expect the processing of temporal features of speech to
Amber?
happen? Like, temporal,
Oh,
so
temporal.
for example, duration, both onset time, and then also on the bigger scale, the adjustment to the speech rate.
Yeah, so I think, so we have these two laryngeomotor cortices. What is the ventral one doing? In non-human primates, it's doing other kind of things, like it's important for eating. You gotta mess with your larynx to make sure you don't, if you can swallow okay, things like that. Also lifting, close your larynx when you lift, things like that. I think for us, it does have a role in speech, in terms of like voice onset time. So basically, it's kind of an on-off switch in the larynx that's controlled by the ventral system. So in terms of temporal stuff, like the voice onset time, I think there is a role for that. I haven't thought about speech rate at all. I mean, I've thought about it, but I haven't tried to work it out. I don't know how that works. So yeah, good question. I don't know the answers. Okay, so that's basically that, okay? So I've talked about this area in terms of its role in pitch control. I think of what's happening at the lowest level. You have the dorsal laryngeomotor cortex directly controlling the nucleus ambiguous, which controls the larynx. You have a higher level of planning, which is something in between prosodic phrasal level planning and low level motor control. So you have this hierarchy. Okay? And I've talked about this exclusively in terms of pitch, because that's where the evidence, that's where we have evidence in terms of like Eddie Chang's work and so on. But if I'm talking about prosody, and I think that this higher level area that seems to be implicated in syntax is implicated in syntax because of prosody, which does play syntactic functions, phrasal, chunking, all sorts of things like that. But both prosody and song involve rhythm as a prominent feature. And so the question is, how does rhythm fit in? Okay, so that was the next thing I was interested in. And that is a conjecture that we put in at the end of the paper on this beyond Broca stuff, which is this: the rhythmic synchronization, the ability to synchronize movement to an auditory beat, is a necessary function enabling the coordination of the two proposed vocal control streams. So the idea is, if you have these two streams, they need to be coordinated in speech production. You want to put the syllable accent at the right timing point as you're speaking. And there's evidence that that's very precisely timed. So in order to coordinate those two streams, you need some sort of a coordination mechanism. And the idea is that rhythm is kind of the conductor, just like an orchestra has a rhythmic conductor to keep all the instruments aligned temporally. The same thing is happening in speech. That's the conjecture. And I know at this point it was really just maybe this is happening. But I've started to look more carefully at this, which is what I'll talk about in a minute. But before I do, I want to comment on sensory motor architecture, and the scare quotes are there because when I say sensory motor, it means something to me that's different than what it may mean to you. So if I say we're talking about sensory motor control or a sensory motor circuit, you're probably thinking fairly low level in terms of relatively low level motor control and kind of lower, kind of sensory control at relatively low level. So auditory as opposed to, say, linguistic, right? When I say it, I think of it in terms of homology, that you can have a sensory motor architecture that would be important for directing saccades or whatever relatively low level things, but that same architecture, sensory motor like architecture, applies at higher levels of planning as well. So just to illustrate, here's how I think of sensory motor control. So all sensory motor control involves sensory systems. That is, the sensory system defines the target of the action. Just think of reaching for something. You have a visual target. If you were to reach for it, you would use the sensory features of its location, its orientation, its size to execute an appropriate grip, okay, as you reach for it. So that provides the target. You have planning, that's motor coordinate kind of planning. I'm going to move my arm, shape my hand. And then you have some sort of a translation system that's computing the relation between a sensory representation and a motor representation, okay? That's the basic idea. You can make this hierarchical. If you have different levels of planning, you can imagine a hierarchical system that looks something like this, where you have different levels of the hierarchy, each doing its own sensory motor like transition. Okay, does that make sense? Okay.
It's a bit abstract right now, I mean, he's.
Yeah.
Yeah.
So this is a particular one that I've developed for language. So I've flipped it on you. Higher level is now down here, sorry. This kind of reflects it doesn't matter. So here's the phonological. I first worked out the phonological sensory motor hierarchy, where in auditory related cortex, you have sensory, like auditory related phonological codes that serve as the target. So you have a word like ukulele, and that you have a representation of what that should sound like. We can mess with that. I can tell you it's not actually pronounced ukulele, it's pronounced ukulele. If you want to go to Hawaii and talk to people about it, that changes your sensory target. And now you can say that word like a Hawaiian would, ukulele, because now you've updated your target. There's a translation system that you've learned during development, how to translate sounds to motor, speech, and so on. So the regions involved are those regions that have been identified in the map that I showed you earlier. Auditory related areas, a portion of the back part of the Sylvian fissure called SPT that does the translation, and then motor planning in the dorsal and ventral regions. Recently, I've argued that the same architecture holds at the level of syntax. Okay, so you have targets, which are basically hierarchical representations of a phrase. This is getting way far removed from auditory, but just to show you that the architecture still holds. You have a linearization process involving parts of Broca's area and other regions. We're still working on that. And then you have a kind of transform system in the supramarginal gyrus. Okay, so this is an example of a kind of hierarchy where you would have sensory. So when I say syntax is basically sensory motor based, linguists freak out because they're like, no, this is abstract, it's syntax. And I say, yes, it's abstract, it's syntax, it's whatever your linguistic theories say is going on here computationally. But the architecture that it's grounded in is sensory motor. It is, and I think of it in evolutionary terms, these systems evolved out of lower level or other kinds of sensory motor control. You had a duplication of a sensory motor control system that could then evolve in its own way to do a different function like speech, scaling up to syntax. Yeah.
Is checking that what you've pronounced is what you wanted to say part of the system?
Yes, this is part of, so this is, I think of these in terms of standard motor control. And it's certainly the case at the level of phonological planning. You're starting to say something like vertical, and as part of the planning process, you activate the sensory target, you activate a plan, and before you even say it, you check to make sure that this plan is going to hit this target. Evidence that that's actually happening in your brain is that if you damage this system, speech errors go way up. You can still activate these things, but you can't check them. You can't error check them before they're produced. And so your speech errors increase. There's also evidence in speech errors in healthy people where you can detect and correct an error before you should be able to, if you were relying on overt feedback. So the example is a speech error like it's horizontal line. So by the time you heard the coming out of your mouth, see if you just do the math, there's not enough time to do that correction. You must have detected it earlier and started the correction process. A little bit slipped out, but you were already corrected. There's other evidence too, if you're interested. So yes, that's part of the planning process. So there's two kinds of feedback control. One is internal, before you even produce it, and the other is external feedback. You can hear yourself talk. Okay, so this brings us to the other part of the question.
Yeah, yes, it's not clear to me. So there are two two targets basically. One is top down and you compare it with your internal prediction from the motor, right? This is the first one before you even speak.
Yeah,
And then you have a second one. So if this was correct, like your model plan was correct, then you speak and you compare again, right?
yeah, it's the same target, but yes, there's
It's
two,
the same
there's two
target, so
mechanisms.
when you generate top
Exactly.
down,
Yes,
which is down is the.
yeah. So people with damage to this system, this SPT area, they have a syndrome called conduction aphasia. They make a lot of phonological level speech errors. And they'll produce the speech and they can detect that they've made an error once they make the error. They'll say, it's a Koki, no, that's not right. And they'll know that they made the error. So what's happening is they make a planning error, they can't check it. The error comes out, they then hear it, and they compare it to their intact target, which they correctly activated and know that it's not the same. But they can't fix it because they don't have this connection.
Georgia is asking, seems like you have two targets. I mean, where does the first auditory target come from? Is that from? The
Yeah,
planning of the
so
model?
it comes from, so you have a concept, you want to say a cat, yeah, you're thinking about it. And you access a high level word, we call them, in psycholinguistics, we call them a lemma, or a lexical, or a morpheme, part of morphological processing. So it basically comes from this flow of information. You have the concept, you activate its abstract word form, you activate its phonological code, which is auditory based. Simultaneously, you're going in this direction in parallel because you've learned how to produce all these things already and you can directly activate it.
Memory store of everything, not just semantics, it's pronunciation.
Yeah, so this is
auditory.
basically a model of the language network, a very sketch level model, conceptual representations, morphosyntax, phonology. This little box here is involved in comprehension. The whole thing is involved in production.
But then, does it make sense to have like the motor hierarchy, like the motor planning hierarchy on the other side? I mean, if you generate the targets already on the sensory side, it's enough just to have the.
Well,
logical
yes,
or-
so you definitely need levels of the hierarchical planning.
Okay, because you produce targets.
You produce targets at multiple levels and each of it's doing its own thing.
Okay.
Yeah, and coordinating everything. And then this, the phonological part, what I've argued just now, is that this isn't just one, there's separable hierarchies for pitch related prosody, that kind of thing, and for phonetic level.
Prosody would be a very high level, because it's.
Well, it's gonna have its own, so there's, I did this before I worked on this prosody stuff. So there would be, at the level, so prosody is a component of phonology. It's part of suprasegmental phonology, as it's often called. And usually people think of it as a completely separate system, but for me, it would be like parallel systems at the phonological level. This was developed in terms of like syllable like planning. Okay. Great question, but I do want to talk about this because I think there's some experiments in here that could be done. So, right. So rhythmic synchronization, it's a paradoxically rare trait that humans can synchronize to a rhythm. If I play a metronome, you can clap to a metronome, tap, move your head to a metronome quite well. Humans are really good at this. With basically, if you're tapping to a metronome, you have a 0 delay in terms of your ability to tap on the beat. Okay, which seems obvious to us, but if you ask a monkey to do it, they can't do that. They can tap to a beat, but they tend to be behind the beat by a couple hundred milliseconds. Okay, they're better than basic just reaction time. This is their simple reaction time. So they're learning something about the rhythm, but they can't get to the human level, which is a 0 delay. Yeah.
What about parrots? I thought parrots were.
Okay, we'll get to that video. So this is paradoxical because in general, physical systems synchronize if they're connected. Are you familiar with this video? So these.
No, go ahead. Please.
Yeah. So.
Cooper always pointed out that people made a big deal that they synchronized. Says, oh, what is interesting is preventing it from synchronizing.
Yeah,
That's
right,
the hard thing.
yes, yes.
Preventing it from synchronizing.
In fact, that's true. So these are connected because they're connected via this platform, which can move back and forth. And if you let it run for a while, these things will just synchronize.
They will have the same, period. Yes, right?
Yes, that's right.
Yes, yes, yes.
Yeah, so
But if they didn't, they will still synchronize over longer.
Yeah,
Suppose you have twice.
yeah,
the amount.
right, yeah, I don't know. This is just to illustrate that things tends to synchronize. Synchronization is common in that, I mean, we think of neural oscillation synchronization, or just timing to a beat. You recorded from monkey auditory cortex, it would synchronize quite well to that pulse, and yet they can't get their motor system to do it, whereas we can. So what this suggests is that our auditory motor systems are coupled, whereas monkeys, it's not. Okay, that's the logical implication of this. Parrots do seem to have this coupling.
Yeah, go snowball.
So we've got two out of sync speakers, but you get the idea. You can Google Snowball the dancing parrot if you want. This was a YouTube thing for a while. Ani Patel and John, I don't know if he's here, but came across this video and said, is this animal truly synchronizing to the beat? Because humans do this quite well. We do it predictively. Is the parrot doing it predictively? You can find an animal that tends to move at a particular frequency and then play a song at that frequency, and it looks like they're synchronizing, but they're just moving at their intrinsic beat. So you have to make sure it's flexible to change the tempo. Can they synchronize to the change tempo? So John Iverson and Ani Patel contacted the owner, went out and tested Snowball, and published a paper saying, yes, in fact, Snowball can synchronize to a beat. So that is
I'm sorry, you make it sound like it's just this noble parrot, but any parrot.
yes, it's been documented in other, parrots can do it. So humans and parrots. It has not been demonstrated. No, this is spontaneous. It's spontaneous.
I thought the owner spent years
Playing
music.
playing-
with,
yes,
tapping.
Playing music. This isn't a wild behavior. You don't see parrots
No.
dancing in the wild.
Well,
But-
never showing us.
But neither cockatoo, neither do you have, systematic rhythms in the wild either that would induce this.
Say that again.
Neither do you have music in the wild or something that's systematic.
Music is as old as we can go anyway.
Yeah, but it's not in nature. Yeah. For humans, yes.
Not ever anybody seen a parrot do anything like this in the wild.
That is true. However, it is an ability that a parrot has. Monkey's never seen it either, and yet they can't do it, even with training.
See lions do it.
Yeah, okay, so there are other creatures. So let me talk about where this ability might come from. And then we'll talk about the other species. So what's interesting about parrots is they can speak, right? They are coordinating, unlike songbirds who are just using their syrinx to learn, their vocal learning is limited to the syrinx. Parrots coordinate both the syrinx and their suprasyringeal vocal tracts. They move their tongue to articulate speech, so they can use both of those systems. There's some evidence in the parrot brains that there are two separable systems. It's not been studied extensively, and I've talked to some bird people who say they don't believe that, but maybe it's true that there are two separable systems in parrots, two separable song systems that might correspond to syringeal and suprasyringeal control. That's the idea. It's still being worked on. So the connection then is what people are really interested in. Ani Patel and others and me now are interested in why is it that parrots can do this and we can do it. We both speak. What's the connection? Other species, sea lions, seals, there's some evidence that they might be able to synchronize as well. In addition, those species do have vocal learning. You might Google Hoover the talking seal. So if they have vocal, the prediction is that if an animal, a species has vocal learning ability, and two systems, larynx and a supralaryngeal, they should be able to dance. Move to a beat, yeah.
What do you call speech?
What do I call speech?
Yes. I mean, parents wouldn't be with conversational partners, I suppose.
No, speak, what I'm meaning is just the ability to articulate speech, just to learn words, not meaning, not higher level things. Thanks for the question.
So you don't know the answer to this, but do parents in the wild say complicated things?
They're understudied. I have the same question. So like, what are they actually doing in the wild with all this speech?
And why did they develop these two systems they never used?
I don't, they're very social. They have a lot of communication. My guess is that they've evolved, they've evolved this ability to coordinate these two systems somehow. I'm not sure. The answer is I don't know. But it's
to say that just because they're using the vocal tract as a physical plant, doesn't make it any more special than using the arms.
That's right, and a lot of animals have voluntary control of their vocal tract, and parrots, if you watch them, they're really good with their tongues and beak to get at nuts and things like that. So that may have been just a motor control ability for getting at food. Right. So, but they have pretty good voluntary control of it, and then they evolve into being songbirds. I don't know which came first. And so now they've got control of two systems. And those things, for some reason, they need to be coordinated in this species. So the prediction is that there's got to be some coordinated function in parrots. That's what I would predict, that they're using in the wild that required the coordination of these two things that led to this.
So, I mean, what you're saying sounds reasonable, but it's surprising that you got two different parts of the brain for two pieces of the body that are so close together. Are there other motor systems that are split like that?
Yeah, there's an interesting thing about motor cortex. It used to be thought that motor cortex is kind of like a piano, where each note corresponds to a different body part, and when you coordinate it, you play. Yeah, that doesn't seem to be the case. It seems to be more functionally organized. So you can have, if you look in macaque, you have multiple hand representations. But if you stimulate it in the right way, you can show that they're doing different functions. So there's like a hand area for swatting and a hand area for bringing to the mouth. That kind of thing.
What's part of this too?
Yeah, something like that.
From your stomach.
Yeah.
Okay.
Something like that, maybe. But yeah, so I think it makes perfect sense that there's like two laryngeal motor cortices. They're different functions. One is ancestral and one is derived. So for a different function, one's controlling the larynx for pitch, rhythm maybe, I don't know. And the other one is involved in.
I mean, I think your argument, sorry, to me, well, I think your argument is saying two different things. I mean,
Okay.
the piano version was just that the two areas makes perfect sense because you have some keys on one part of the brain and some keys on another part. When it's all mixed up together, your argument, that was just that all should be one distributed network.
One distributed network. Well,
One distributed representation kind of functions.
I think it's. Yeah, maybe the analogy is not that good. I think that motor cortex is being functional and organized around a particular goal. So laryngeal control for pitch is one goal. Laryngeal control of lifting things is another kind of control. Two separable motor systems for doing that. When you have a system like that's controlling pitch for higher level behavior, like generating prosody, now it's part of a hierarchy that's doing something a little bit different at multiple levels of control. So yeah, I mean, I don't understand the details of how these systems work. I'm just kind of starting from the big picture and trying to see how close I can get to that.
Hey, Greg, sorry, quick question.
Yeah.
A little bit orthogonal, but I think we all get how ChatGPT and LLMs can be useful in giving answers to questions. How could beat and rhythm be useful? Any thoughts? Apart from music, of course.
Well, beat and rhythm are really important for coordinating speech. I'll talk about, in a minute, I'll show you examples of where rhythmic deficits lead to speech problems. Okay, so maybe that will help, at least in the speech domain. Because I'm arguing that all of this beat, rhythm, dancing ability comes from speech. It's the need to coordinate these two systems that led to the use of rhythm, that led to, fortuitously, the ability to dance. Okay, so let me detail that argument. See if it answers your question. So what is the relation between rhythm and speech? So Ani Patel has one story. Basically, parrots just have stronger connections, and that leads to this ability. So it's not a coordination issue. I'm going to suggest instead, like what I've just been saying, that it involves two separate networks. In order to synchronize them, they need to be coordinated. So let me give you some of the evidence. So synchronizing involves auditory-based quasi-rhythmic targets. This is where it gets interesting because speech is not like music or simple beats. It's not rhythmic in the same sense. It's quasi-rhythmic, and you can see that if you just clap along to the syllables. John wrote a rough draft and edited. So there's a rhythm there, but it's not like a musical beat that you can dance. This is why we don't dance to speech. You're not compelled to dance as I'm talking. It's not predictable enough.
Allow rapping?
Rapping is different. So can the auditory system actually code quasi-rhythms? Because this is so if I'm arguing that you have targets that are sensory based for every level of planning, you've got to have, according to my thinking, a rhythmic target in the auditory system on the sensory side somewhere. Can the auditory system code these things? The answer is yes. For time's sake, I'm not going to detail that. So here's the idea. When you're planning a sentence, one level of planning is a prosthetic, acoustic, rhythmic frame. So you have, if this is the sentence you're going to plan, you're planning a phrase, Juan wrote a rough draft. You basically have an acoustic code, somewhere in your auditory system. That's the rhythmic code that's used to plan a prosthetic frame, that's used to then slot the syllables in. Okay, that's the idea. So disruption to this plan can mess with things. Is there evidence for rhythm affecting speech planning? You're familiar with the delayed auditory feedback effect? You delay speech by about 200 milliseconds, it disrupts fluency. It's typically thought, so here's party, you're speaking it, you hear it delayed by 200 milliseconds. That's about the syllable duration. So it is usually thought that the reason this is interfering is because you're expecting to hear T and party and you hear par. So a mismatch of the syllables, the content of the syllables. But notice that there's also a mismatch in the stress patterns, party. So you're hearing high-low, and then you're hearing the opposite. So which of those things is driving the interference with speech? I won't go through these details, but the answer is it's the rhythm. It's the stress patterns, not the content. Okay, that's the answer to that. If you look at neural responses to delayed auditory feedback, interestingly, you get the highest density effect during delayed auditory feedback in this dorsal precentral speech area. Circumstantial evidence, I haven't worked out the details yet, but an interesting fact. Okay. Speeding up. You've heard of the KE family who has FOXP2 deletion and basically childhood apraxia of speech. They congenital apraxia of speech. Okay, they're bad at rhythm. Simple rhythm.
So in the experiments, the feedback is delayed?
In these experiments, yes, feedback is delayed by about 200 milliseconds. And this is just showing neural activity ramps up in in a lot of places, including auditory cortex, no surprise. But it's more highly concentrated in this dorsal precentral speech.
So it's the timing of the predicted signal.
It is the the details of what's actually.
200 milliseconds.
It's 200 milliseconds is the delay. That's just the physical stimulus.
5 hertz. The sweet spot.
Yeah, exactly. Right. What it's actually computing, what does this activation reflect? I'm not sure.
Well, I think you said it's like you're trying to predict something different from what
You're trying to, yeah. So basically, what happens with altered auditory feedback generally is you're getting prediction error in auditory cortex. A prediction error will tend to want to be corrected by the system. So some correction signal is going up here. This may reflect attempts to correct or do something or just general interference. I'm not sure. So KE family does have simple rhythm problems, just tapping to a beat. Interesting. There's other evidence. Where am I going here? So usually if you talk to the music cognition people, they will tell you that synchronizing to a beat enhances your perception of the beat. Right? Okay, so and there's evidence like this. you have an isochronous beat. This is, isochronous means the pulse is coming at exactly equal time, but you have one high pitch and three low, one high, three low. So you get this rhythmic kind of pulse. And then the task is you get a probe tone after you've heard this beat and you decide whether it's on or off the beat. If you synchronize to the beat by tapping to it, people are better. Okay, so that's the kind of evidence that makes people think that synchronization is that synchronizing to a beat motorically affects your perception of that beat favorably. Okay? I'm gonna argue the exact, that's another experiment, that it actually makes it worse for detecting on the beat. So you wouldn't want me to say something that makes intuitive sense, right? We'll go non-intuitive. And it's based on a motor control. It's intuitive from the standpoint of motor control. Motor control generates a forward sensory prediction, right? So you're tapping something, you're making a sound. I expect to hear it on that beat. Okay. Predictions are generally suppression signals. Think saccadic suppression. Okay. So what that means then is if I'm tapping like this and I'm hearing that beat, I'm less sensitive to the acoustic perception of that beat because of the motor prediction. I will be more sensitive to things that are off that beat. So it actually enhances the perception of off-beat signals. Okay, this is just straight out of motor control theory. So is there evidence for this? Not from those beat experiments, but from some experiments that I did for other reasons. So here's the paradigm. I was interested to know whether an entrained rhythm would affect perception at the beat frequency, at the rhythm frequency. Okay, so this is an AM signal, 3 hertz, 3 seconds long. So that's the entrainment. Your auditory areas are entraining to that thing and oscillating at that frequency. And then we present a tone in the steady state phase at various delays or phase relationships to the entrained beat. Okay, so kind of in the troughs or at the peaks. And then we have people detect whether a tone occurs in this period here and ask whether detectability oscillates at the beat frequency. Yeah.
Would it be true to say that if this effect is, or if the mechanism is what you think it is, that you should see that more by singing to the beat than by tapping to the beat, because that's more directly.
Maybe, yes, yes, I think maybe. Yeah, we weren't looking at it in connection to the ideas. I'm looking back at this experiment thinking, oh, this is a motor prediction. I didn't know that at the time. But so here's the results. This is detectability as a function of phase delay. This is the phase of the entraining stimulus. One thing that surprised me, I mean, it was remarkable that we got pretty big shifts, 70 to 15, sometimes 25% changes in detectability of the tone. Yes?
So what do you mean by detectability? Just that
Oh, it's a simple tone and noise detection test. D prime. Or this is proportion correct, but D prime shows the same thing. It's out of phase, almost 180 degrees out of phase with the entrainment stimulus. That didn't make sense to me based on the rhythm experiments. We didn't really know what it meant, but it is out of phase. It makes sense if this effect is coming from motor prediction. You're basically generating a rhythm that you're entraining to your motor system. And note that people do claim, and I think it's probably true, that if you hear a beat, it automatically engages your motor system, of which if it's engaged will generate a forward prediction. And possibly what's happening is not an enhancement of detectability, but a suppression of detectability of things on the beat.
You know the story about the wobbly bridge in London where basically people walking across it, if you had enough people, they would entrain to each other.
Oh, yeah.
And then the bridge would start wobbling, and
Yeah.
so they would entrain to each other more. And then
And then it would
eventually
get worse and
the
worse.
bridge became unstable and they had to rebuild it.
Wow.
I mean, it didn't fall down,
Yeah,
but they
yeah.
had to change
Yeah.
the dynamics of it. So what is it? Why is it, if that's happening in the motor system anyway, right? This sort of natural, because we have other things that naturally have a beat, right? Central
Yeah.
matter generators and all these things.
Right.
Why is it necessarily the speech that's doing it for us
Great.
rather than these other things?
Great question. I have the answer to that. That's why it's paradoxical that most animals can't dance, or that's the mystery. So what you're talking about is something a bit different. If you do those rhythmic and tapping experiments to a flashing rhythm, you are not as good. It's auditory specific. So it's not, auditory is special, it's better,
But
but the walking.
isn't physical
Yeah.
like,
So
it's
yeah,
a cross between auditory and.
well, yeah, so I think people tend to synchronize their walking paces, right? If you just watch people walking, they will tend to synchronize their steps. That's been an observation. Why is that? I think that's auditory. I think they're hearing the footsteps is driving a tendency to want to synchronize. You laugh, Shihab?
Yeah, so I'm curious, this experiment didn't involve anything motor. You didn't
No.
ask people to
No,
tap and all that stuff.
That's right.
So why do you assume that the motor was involved? It could have been very well that rhythm is also to be auditory stored.
Yeah.
And it predicts the
Yeah.
same way, just
I
that the
don't-
motor does.
I don't assume. I hypothesize. I didn't know, when we did this experiment, we did follow-up experiments, determined that this is probably an attentional effect, not a bottom-up effect. And so we left it at that. It's attentional.
And you have to be, you have to attend to it and do it.
Sorry,
You have to be attending to it.
you have to attend to it, yes, and it has to have, and yeah, there's various, you have to attend to it. We wrote another paper and then a review paper, no inkling that this was motor based until I started thinking about rhythm. So I've gone back to think about the hypothesis that this effect is coming from the motor system. It's a hypothesis. So what we're doing now is testing to see if we can get the same perceptual effect with people tapping, no auditory signal at all, but just people tapping to generate a motor prediction that should affect the perception. So we're doing the experiment to test the hypothesis. Doesn't have to be motor, but that's my hypothesis. This is direct cortical recordings in the same task, showing that the gamma signal does not do any prediction, and I'll just blow through this, but the theta signal does, which if you think that theta is a higher level, larger cortical circuit signal, you do get a predictive effect even after the stimulus disappears.
So it's around 5 hertz.
So we've done experiments to see what the range of beat intervals that we get the effect. We get it at 2, it cuts off at about 8 hertz. You don't get the effect. Okay, I think I'm about done. There's some other stuff to talk about. So this is just a fun thing. I'll end on this. So syncopated rhythms. People study syncopated rhythms. It's called groove, songs that make you want to move. If you look at songs that make you want to move, they tend to be syncopated. First, that means you have a dominant beat with an accent that's in the middle, right? So yeah, that's syncopated rhythms. Why the extra urge to move? So think about this in motor control theory. Dominant beat generates a prediction, increasing the prominence of deviations from that prediction. So you're moving to the dominant beat. Listen to Superstition. Starts out, Stevie Wonder. Starts out with the dominant beat, and then when it gets going, the syncopated rhythm comes in, and it really makes you want to move. So you're synchronizing to that dominant beat. You increase sensitivity to the deviations, which makes those intermediate ones really prominent. So, but that's an error signal because you're moving to the dominant beat. What happens then is deviations tend to want to make corrections to the movement, which generate another movement, and you kind of rinse and repeat. So there you go. So possible explanation for group. All right, I will stop there. Yeah.
Yeah, this is just kind of my perspective on why neuromorphic is promising for machine learning. So these are principles that I think we're all familiar with. So massively parallel processing, low precision computing. So you communicate in spikes or in sparse values and low precision values. An additional thing is that you have sparse and recurrent connectivity, and that gives you kind of these like modular, nearly decomposable systems that are quite interesting. And then you also have these sparse activations that are not really well covered in most of deep learning, but kind of getting there with mixture of experts, which, yeah, Owen will be talking about at some point this week, I think. Yeah, so there was already a brief introduction to state-space models in the topic intro for this topic area. The basic idea is very promising because it's state of the art on a lot of long-range sequence modeling tasks. It scales more efficiently than transformers. So in transformers, you have this quadratic self-attention block, which scales quadratically with the sequence length. And if you use a recurrent network, then inference is always constant. So you always pay the same price for predicting the next token one step at a time. And it has recurrent dynamics, which all of us love because we're doing neuromorphics. And they may also be promising for continual or online learning. So there's a paper that I'll just briefly sneak peek. The general picture you should still sort of remember from the intro talk. So you have this discrete time recurrent system. You also have a continuous time system where all of this actually comes from. You can discretize this, and then this gives you efficient inference. But since the state space models are just linear, like LTI systems, you can also express them as a convolution, and then that's very efficient for training. So you can parallelize your inferences or like your training. So I'll talk about this as the recurrent mode and the convolutional mode. The core model is pretty simple. So you have a hidden state at time t, you have a recurrent matrix A, and you have an input projection matrix B. So these are A, B, C, D, that's the standard notation. And then the output of the state space model block goes through an output matrix. And sometimes you also have a residual connection that goes from the input directly to the output. So X is input, H is hidden state, Y is output.
What are the dimensions usually of these X's and?
It depends a lot. So
512, 1K, 2K, etc.
yeah, something like that.
And isn't this basically just the same as exactly as a vanilla RNN?
It is if you make it recurrent. If you
But
make it
with
linear, sorry.
linear vanilla RNN.
Yeah, exactly, a linear. But
Oh, it's not recurrent here so far.
no, sorry.
Okay.
It is recurrent, but yeah, state-space models are linear. So you don't have any non-linearity in the here.
Linear vanilla recurrent.
Yeah, exactly.
Okay.
And the way that you're also parameterizing it is usually you have these ABC that are coming from the continuous time system. And then when you discretize it through zero order hold or some discretization method of your choice, and then you get these discretized parameters. And this is then what's passed into the SSM when we actually run it on digital hardware. And you often also have this timescale parameter, which you can use to kind of rescale the timescale of your state space model. And yeah, so these are then the parameters that you learn, the timescale, and then the ABC, or sometimes A is also called lambda, and sometimes also the D if you want this residual connection. And yeah, so in a lot of the projects, I think we'll work with deeper architectures. So the main insight now for scaling up state space models is that a simple linear recurrent network is not that interesting, right? It will not solve any relevant tasks. But the insight from these like state space models in deep learning is that you can isolate the recurrent into a linear recurrent unit. So this is the state space model. And then you put the nonlinear mixing, the MLP channels basically, and then you stack them. So you have a linear recurrent, a nonlinear dense layer, an MLP.
Saturation basically, right?
Yeah, exactly. Yeah.
Or rectify.
Yeah, it can be a ReLU, it can be whatever you want really. And then you just stack them. So you take one of these layers that has the linear recurrent and the MLP, and then you can stack them and you can make deep architectures. You can stack 6, 8, 60, depending on what task you're doing. And then you also have these kind of linear encoders and decoders from your input to output. So this is the general kind of architecture. Now I have a very dense slide where I didn't get to actually add pictures, but yeah, bear with me. The LMU, I think you already were kind of presented. So this is where it all began. And it also has roots in neuromorphic, and we're all very proud of our neuromorphs. And yeah, this was at least to my knowledge, and I think the general consensus is that this is kind of the first time that the state space model was developed for machine learning. It was based on these Legendre polynomials. And then 1 year later was the Hickok paper from Abreu at Stanford and his colleagues. And they generalized this framework into just a general framework for state space models based on structured matrices. So these Hickok matrices are structured matrices. There's a whole theory around it. It's a long paper, it will take a while to read. And yeah, the point from later on is that you don't need to read it anymore, but we'll get to that. S4 was then the first deep architecture based on the Hippo framework. S4D was then an interesting follow-up paper that showed that you can actually make the SSM work just as well with a diagonalized A matrix, which is kind of surprising because that means that every recurrent unit in your system only talks to itself. And yeah, at least to me, at first, that shouldn't have worked, but it actually does work. So now most architectures are actually diagonalized. Then the S5 paper simplified the architecture quite a bit. So up until then, all of the state space models were expressed as a single input and a single output. So you don't have vector inputs. You just have a single input dimension and a single output dimension. And if you have multi-input, so for example, if you do sequential image processing, you have RGB channels, you process them all in parallel, and then you have a huge linear mixing layer to mix the information between these. And the S5 paper simplified that to basically go from a single input, single output to a multi-input, multi-output block. It still uses a similar kind of initialization, and it also scales very well. I have separate slides to actually explain everything that's, or most of the things that are highlighted in bold. There's another slide after. The LRU paper is also very interesting because that's, yeah, the point of the LRU paper, at least to me, is that you don't need to read Hippo anymore, and you don't have to care so much about this.
Is LRU what you describe the matrix?
LRU is this linear recurrent unit. So it's a paper by DeepMind, and they basically try to investigate if you can just use standard deep learning techniques to replicate the success of state space models. So without this Hippo theory, can you just initialize it nicely, normalize nicely, and parameterize your parameters nicely so that the optimization works and you can recreate the results from all of these?
But why do that if you know that you need these triplet matrices in the first place?
Because apparently you don't need them.
But why? It's so easy to do that. Why not just do that, right?
I mean, you can still do that.
Okay.
Yeah.
No, but I presume this can find a more general Fourier solution.
No, I don't know if that's showing though.
Because, okay, we'll see.
Yeah, I mean, it just showed that if you initialize it in a certain region of the parameter space, and if you parameterize it carefully, and if you have normalization layers, so all the standard kind of deep learning blocks pieced together, then you get to the same output. So to the same results. Sorry.
That's fast.
As fast, yeah.
What is parallel scan?
I have a slide on that, yeah. But yeah, so the main point is that basically all of these were they trained these models in convolutional mode, like we showed just before, because it's just an LTI system. For S5, it's not easy to come up with this convolutional representation. So they actually use parallel scans. And I should have put a slide on actually parallel scans, but I have a similar slide that's like kind of towards parallel scans. And yeah, the latest innovation right now is came from this Mamba paper, where they call Mamba a selective state space model. So the problem with normal state space models, and I think also one of the reasons why they never performed as transformers on language modeling tasks, is because every single input token you'll treat at this like in the same way. There's no context dependent gating in the input matrix. So you always have the same B matrix to project your input into the hidden state. But sometimes you may know already that the current token, based on your previous tokens that you've seen, the current token is not relevant, like you just don't want to add it at all, or you want to overwrite something. So you may want to have this input dependent gating behavior. And this is what the Mamba paper did, because they just made these matrices vary with time. So instead of having a single A, B, C matrix, you make them vary in time according to some dynamics.
Some pre-handcrafted dynamics.
No, they're also learned. Yeah. I have a separate slide on that. This was just a very dense, overview.
Oh, I see.
So this is the S5 model. I'll get back to it again. I picked it now because there's a couple of things that it does that I think are important and that I'd like to highlight. So one is that it's diagonal. So this recurrent matrix is completely diagonal. So it's basically just a vector of the same size as your hidden state, which you can see here. It's complex because if you want to diagonalize a real valued matrix, you can diagonalize it in complex space, and basically every matrix you can approximate it this way. So that's and the picture then that emerges is this. You have this input projection B, the output projection C, and then you have a bunch of independent recurrent units that only talk to themselves. And they talk to themselves with a complex state and complex weights. So you don't just have a simple decay, but you can have nice oscillations, basically, that encode some information.
And they also have recurrent connections from everybody in the same layer?
They don't
No,
talk to each other.
They don't talk, okay.
No, because
You only get input from B.
exactly, you only get, so you have some mixing between the different inputs. And so every neuron here gets inputs from all the inputs, but in the recurrent dynamics, it only talks to itself. It does not know anything about what the others are doing.
So it's like multi-head in B? I mean, only piece of B?
Yeah, you can think of it as like multiple heads, I guess, yeah.
So it's still learning a residual, right? There's a skip connection.
Yes, you can also still keep the residual, yeah. And often the residual, for example, in S5, the residual is also diagonal. And you don't really need it so much. But it's still nice also for the gradient flows, just residual connections are good.
Are there any special thing about initialization or randomly with everything?
So in the S5, they adapt a similar, so because it's multi-input, multi-output, they can't use the normal Hippo initialization, but they use kind of a variant that they show is a natural way of expanding it to multi-input, multi-output. So it's still using basically Hippo theory. But all that's written here also applies to the LRU, the linear recurrent unit, where you don't have fancy initialization. You just have some conditions.
What's the spirit of the Hippo initialization? It's like getting a sensitive output of something to avoid exploiting advantage.
It's very similar to the LMU paper. So you have just a different basis, and you can choose basically which polynomial basis you want to choose. Okay, so now I promised I'll talk about the parallel scans. This is not an explanation of the algorithm itself, but I'll try to do some hand waving to get there. So the normal S4 picture that people have been using is that you have these kinds of parameters, you set up your state space model, and then you create this convolutional kernel, which is basically a kernel over the entire sequence length. So it's a huge, gigantic kernel, but then you can apply that and you can get nice GPU, TPU acceleration for it when you apply the kernel on your input sequence. And you do this by because convolution in time domain is the same as multiplication in Fourier domain. So you do fast Fourier transform of your input, then you apply the kernel, and then you get the output, you do an inverse Fourier transform, and then that's all very efficient. So it's similar to transformer training where you can parallelize it and really take advantage of the hardware that we have for training. And then since the convolutional mode is exact to the recurrent mode, once you've trained the parameters, you can just unroll and do inference in the recurrent mode. Or if you want to do batch inference, you can again do the convolution stuff.
Is there any padding business you have to do, or?
Depending on your input sequences. There's some padding, and then like depadding.
I still don't get how you go from those very long kernels, linear kernels, to a recurrent network. What do you mean? Say you have to re-roll, not unroll, re-roll, like to get the recurrent network to do the same thing as the linear system, right? Well, basically, I say since it's linear, just multiply together all those operations.
Yeah,
Just
I-
multiply them all together, okay.
Yeah, I don't have the slide for it, but it's basically like
Yeah.
to get the first output, you apply the A matrix one, the B and the C matrix ones. And then for the second output, you do A squared, then the A to the third and so on, because it's a linear system.
Okay.
Then you can construct the big kernel like this, but yeah, applying the convolutional mode is the same as doing it in recurrent mode because the parameters are the same, right?
Thanks.
I mean, they can't always be impulse responsive. You can just write it by impulse, so that you can. I'll go over the.
Okay, and now if we can't do the convolution, so in S5, they're just it's difficult to come up with this like convolutional kernel. Later on, you cannot come up with this convolutional kernel anymore. For example, with Mamba, when you make these matrices time varying, then you need to use these like parallel scans. And yeah, the parallel scan is basically just an efficient implementation of the recurrent mode based on prefix sums. So you get this kind of like logarithmic complexity where you can combine the A matrices kind of bit by bit. So if you think about the kind of an adder circuit, like where you have this like logarithmic, like adding, carrying, and so on, it's kind of the same thing with these prefix sums. So it's just an efficient implementation that doesn't require you to have a convolutional kernel formulation. If somebody's interested, I can send like a good like introduction to how the parallel scans work. It's quite fun, but we don't have to deal with that because Torch and Jax just have implementations for it, so we just use those.
So I know with the convolution kernels, you have to increase your number of hidden states as your sequence length increases. Did S5 fix that?
To increase,
So you know how like, yeah, you're stepping through your sequence, every single step introduces an additional hidden state.
Yeah.
And then you have to just update every single one of those when you introduce your next token. It's kind of like a double, I don't want to call it a double for loop, but you are scanning over time in two ways. And I think that is part of why we've started to move away from convolution kernels for state space models, linear recurrent models. But yeah, I'm not sure when the community realized that. So yeah, I probably have to read S5.
yeah, I'm also not sure right now, but we'll check chat further. Right. Then there's also the move from single input, single output, or SISO, I guess you can call it, to multi-input, multi-output. And the way that you can visualize this is that with S4 and with like earlier state space models, you have your input, which is typically you have multiple input features. And then you have this kind of block diagonal matrix where the blocks are repeated. So it's just the A matrix. And it's treating every single input separately. And then you have this like huge hidden states there. And then in the end, you do this mixing layer where you then mix all of these different hidden states. So intuitively, you can see that this gets quite large. Whereas if you just directly process all of the inputs at once, then you can kind of get away with a smaller hidden state. And another thing that is probably relevant for us is that if you make the connection, like the weights matrices sparse, then you also get an advantage with S5 by doing this multi-input, multi-output, because you have these like B and C matrices, which you can sparsify, and then that scales better with larger state sizes. Whereas here you have this huge mixing layer, and this is anyway large, like there's no way to reduce that. I promised hand waving, you get hand waving. Now we get to selection, because I think a lot of us are also interested in working with Mamba and other selective state space models. So the real move is basically just like you put a T index on the matrices here. Like instead of having a single A, B, C matrix, I'm dropping the D because nobody really cares about the D so much. And you just make these time varying. And the particular scheme that the Mamba paper suggested is that you take your input vector, you project it, and then get a timescale parameter, which then influences the A matrix. So the A matrix is fixed, but for different time steps, you rescale basically the time constant of this A matrix. So that you can make the dynamics slower or faster depending on the input.
Globally though, right? That's a scalar?
No, it's the same dimension, so it's separate for every neuron. In the yeah. And yeah, directly from the X. So from the input, you project that into the B matrix and into the C matrix. So the B and C matrices are completely input dependent.
What are you learning? Are you learning the weights or?
Yeah, you're learning like these projections and you're learning. So I mean, these are determined by the projection matrices here. You're learning basically a C projection matrix and a B projection matrix and the time step projection matrix. And you can also learn the A, like the weights and the recurrence itself.
Okay, can I just ask a question? So with this linear system, you don't really have any memory, except in the activation of the neuron and the fact that that neuron happens to have a very long time constant.
Yeah.
That's the only memory, but you can't like gate that memory. You can't like store something and then erase it quickly.
Yeah, exactly.
You know,
But now with this,
now with this, you can by just setting delta t. If it outputs delta t equals 0, it doesn't change, right?
exactly.
Okay, that's
Yeah.
all. That's the basic gating and memory.
Yeah,
And
exactly.
it's gating and nonlinear gating and memory.
Yeah, and this is this is exactly what
Which
they
is the
show.
magic of RNNs, right?
And this is what they show is crucial to get transformer scale performance on language tasks. Because in language, you have this a lot where you just need to ignore some inputs or pay particular attention to some inputs. And it doesn't help to pay the same kind of attention to every single.
But I have to observe, it's also crucial in like when people build these conv nets to reconstruct grayscale video from GBS input. That's the memory that holds onto the video frame when you don't have any input. It'll stay there for like many seconds, right, with no input at all. Keep iterating it, you know, it's not what a linear system would do at all. It's magical, I think, it's really magical.
Yeah. Yeah, so this stirred like a lot of sparked a lot of interest in the community, this Mamba paper. Interestingly, it was rejected from iClear, so it's just an archive, but that's machine learning.
I mean, the argument was that it was an RNN. It's not wrong, right? It's like.
Yeah.
Argument is just an RNN.
I mean, so it's not novel, like, because people have done this before, right?
So is,
Yeah.
does this do positional encoding?
That kind of comes from your
They
A matrix,
Yeah.
because if you're using a complex A, then you get oscillatory dynamics, and so that's kind of equivalent to, I don't want to say it's equivalent, but it does the same thing as rotary positional encoding. For more reference than this really cute guy gave it to us last week. Might be
Oh, who's that?
I don't know.
Yeah, some related work. I again highlighted in orange people that are here at Telluride, so you can chat with these famous people. So these are just adaptations of state-based models for neuromorphic. The first one is they reformulated the, this is touch. They reformulated the S5 model to allow variable time steps, because usually you discretize with like a constant time step basically, so that you get t+1, t+2, t+3, and so on. But if you have event-based inputs and you have some time steps where there's just no events coming in, then you don't need to roll forward the dynamics of the network, is the idea. So instead, they do this data dependent. So basically, when there's an event coming in, they check when was the last time I updated the states, and then they do this. And with this, you get some more sparse processing. Very cool paper presented at Icons this year. You can check it out. What was his name? Nicola, yeah. He applied SSMs for event cameras and like a big architecture with vision transformers and so on. And they already had an architecture 1 or 2 years ago where they applied just a normal RNN. Now they substituted an SSM into the architecture and it performs better because SSMs are magic. Then, yeah, this paper, yeah, there you are, Mate. So he, with his supervisor, I guess, took this like single in, single out spiking SSM and binarized the activation. So basically put a spike function on it and also showed that there's only a small performance drop on the long range arena, which is the long range sequence modeling benchmark, compared to the S4D, which has full precision activations. So I think this is super cool, and I mean this is kind of what we want to do to put it on hardware. We want binarized or just quantized activations and weights. Now plugging our own work. So this is like Jens, Kate, and I and Alessandro. We worked on this quantized S5 paper where we just quantized the activations and the weights in the S5 model with all the different combinations basically to just see when things break. And just thinking about it, you can probably imagine that the recurrent matrix, like the A matrix, is most sensitive to these quantization errors. I have a slide on that afterwards when we talk about the quantization in more depth. And then Alessandro and I, I didn't introduce myself at all, but I'm currently doing an internship at Intel, and I'm working with Alessandro, and he contributed to the S5 paper, and we also did post-training quantization of Mamba. So for S5, we trained with the quantization in the loop. And for Mamba, we don't want to retrain Mamba because that takes a lot of compute, and we're a bit poor because we're students. So we just want to do post-training quantization without any fine-tuning. And there are a couple of challenges that I'll highlight as well. Now 15 minutes. I'll just briefly mention this. Like, you can look at the slides later and we can chat more in depth if you want. But for quantizing models in machine learning, you can do quantization-aware training, where, just as I said, like you train with the quantization in the loop, and then you can compute these scales kind of dynamically. And this is usually what you do if you can afford it, because that gives you the best possible performance. Post-training quantization is you take a model that was trained in full precision, and then you quantize it after the fact. And then you always get some performance degradation unless you're doing something strange. And here I highlight that just the mismatch in recurrent models is a big problem, because obviously if you have a dynamical system and you quantize the update loop, then the errors just accumulate. Like,
What do you mean mismatch here? Not random mismatch, like
just errors.
quantization
errors. And these like quantization errors just accumulated every time step. And we're talking here about like thousands of time steps. So that's a big error. I have some plots. And you can also do quantization-aware fine-tuning, where you take a full precision trained model and then you just do quantization-aware training for a little bit, but there's no standard recipes for how to set this up. And at least for us, for our state space model paper, this was a bit, unstable. So
we tried this with raw numbers as well, and it sucked.
it's so bad, right? But I don't know if it's just a hyperparameter search thing but I also don't want to spend that much time, so.
But when Shane Gao was training all our delta RNNs, quantizing and weights and activations, he first trained it full precision, and then did quantization-aware fine-tuning afterward, and then he introduced the delta at the end. And this recipe worked really well.
Okay, I should
this
check
recipe
for how the optimization.
Yeah, it was a stepwise procedure, right? First saw the easy one, then quantize it, then introduce the delta at the very end.
Yeah, for us, it breaks in the first step, second step. This is additional details. We don't care so much. Let's just skip that. So now this is actual plots from the S5 model. So I just fed it this like super slow sine wave input, and then you get the real values of the hidden states, the complex, like the imaginary parts of the hidden states, and this is this is quantized. This is full precision, and what I'm quantizing is only the B and C matrices, so only the linear part, like the linear
to some precision
to 8-bit integers. Okay. So I do 8-bit integer quantization, and this is randomly initialized, so I don't even train the network. So these are just random things.
Sorry, I missed what you said. Why not A?
Because A is in the next plot.
Okay.
Because from all. So with B and C, you don't get like if you just look at the curves, they look pretty much the same, the trajectories. And this is the difference, like the absolute difference in the trajectories, the real parts and the imaginary parts, and it's below 0.1, 0.06 or so. So this is pretty good, even for a long sequence of like 10,000 time steps. So BNC is like relatively robust to quantization.
How long?
Now, pretty small. How many stages is this? Like 16 or 8 or so? Like pretty small. Just a little toy problem. And now if I quantize only the A matrix, so everything else is full precision, activations are also still full precision. So I don't quantize activations at all. Only the A matrix, and you get something completely different because you introduce these quantization errors just at every time step. So yeah, this is a problem. If you take a Mamba model and you want to quantize it after the fact, you have to account for the quantization errors that you introduce somehow.
But don't you have the risk of exponential explosions as well? And how do you handle that with these N8, that have very finite dynamic range?
That's kind of what's happening. You're accumulating.
They're wrapping around.
Yeah.
Oh, I see.
That's why the A matrix fucks everything.
Oh, I see.
Yeah.
Okay.
That's what it does.
But when you say N8, is it saturating N8 or not saturating N8?
No, it's actually dynamic quantization. So I'm just as the whatever the range of values is, I take the absolute maximum and then I scale between those uniformly. Yes, like uniform abs max quantity.
How do you get the range? Like first over the floating point, you get the entire range, then for that particular.
For these weights that I have, so I take the weights.
For all the weights, okay.
For all the weights, yeah. I mean, in this case, it's like 10, 20 weights or so.
So it's dominated by the outlier, right? Weight. It's totally dominated by, there's some outlier weight that's very big.
Yeah. In this case, there wasn't because the initialization is bounded. So you initialize it like pretty uniformly. But in general, yes. And you're already anticipating the next slide. No. Well, in 5 slides or so. I think I'll skip this part. If you're interested, the paper is on archive and you can look at the results. But this is where we quantize the S5 model and we do a lot of experiments on quantization aware training, post-training quantization. We look at every single component in here because the goal was really to make this hardware friendly for digital neuromorphic acceleration. So we take every single block, even the norms we have to quantize. We substitute the activation functions for something that can be done in fixed point arithmetic only, and all of these things. So it's really good stuff, really fun. You can take a look. Results are great. Don't look at the table, they're great. Don't worry. Trust me. And this is the Mamba model that we tried to quantize after the training. And yeah, there we have these like outlier problems because you see this as you scale up transformer models. So in general language models, you get these activation outliers where some channels just have gigantic activations during inference. And we plotted these, so in the different parts of the architecture, so these are just all the normalization, the linear blocks and so on of the Mamba architecture. And yeah, then we're plotting that some of them are well behaved. So I think this is like a couple of
time and what is the
so these are the channels, basically the different channels, the features or whatever, and then these are the absolute magnitudes or like the absolute maximum, sorry,
I see.
On this channel across I think wiki text or some data set of text. And then we're plotting just the outliers that are, I think, above like two standard deviations over. And you can see that some are pretty nicely behaved. But this one in particular, we don't really care about. These are the important ones, and you have a lot of outliers. And now if you do quantization, then the outliers will basically push the precision of like low values to very, very low precision, and then you get very large errors, and then you destroy your model. So yeah, we just demonstrated that this is the case, and we're right now still working on fixing this with some ideas of yeah, like existing literature where you can push the quantization difficulty between the weights and the activations, because the weights don't have these kinds of outliers, and you always have a product between weights and activations. So if your weights are very well behaved, then you can just push some of the outlier channels into the weights. And then you make the weight quantization a bit more difficult, but the activation quantization a bit more easy. And then this works for transformers, and I'm sure it'll work for our model as well. We just have to do it.
Is there any intuition about why you see these outliers?
I think there are some like MEC studies that are studying what these outliers are actually doing. We tried just masking them out, like setting them to a max value, and then that breaks the model. And like on the evals, it just performs terribly. So they are important, but I don't know exactly what they do. I don't know. Have you looked into this?
Yeah, I mean, I think all LLMs have these insane outliers. I'm not sure why. But I will say that we tried doing stateful quantization aware training, and for that, clipping the hidden state rather than weights itself really helped.
What helps?
Clipping the state rather
Clipping
than
the state, okay.
weights. It's kind of like after
Yeah.
you apply your weight. I don't know. Has anyone tried regularizing, penalizing excessively large weights to avoid this?
I mean, it's not the weights, it's the activation.
Sorry,
value.
yeah.
Yeah. I guess, yeah, you could try this, but again, then it's a during training kind of thing. Yeah, so this is the best we can come up with for now for post training. Yeah, there's 5 minutes left. I wanted to talk about sparsity as well.
Yeah, let's see.
But yeah, so these are these like delta RNNs that are super cool, where you introduce activation sparsity. So I distinguish activation sparsity, which is what we have in spiking neural networks, where most of the time the neuron does not communicate with downstream connected neurons. And this is very nice. Weight sparsity is what most people in deep learning are familiar with. So this is just you prune connections between neurons. The cool thing is, and there's another paper that shows this, that weight sparsity complements activity sparsity, because I mean, you can just see that if you make the activation sparse and the weight sparse, you get like the two multiply each other in the reduction of operations you have to do on the hardware during inference.
Although I will say that paper showed that the more dynamical activation sparsity you have, the more impact weight sparsity you have on hurting performance and vice versa.
Yeah.
So it did feel like a tug of war. So compliments felt like the wrong word, but it is really good work.
Yeah, it's very cool work, but yeah, we also saw in some experiments that it's difficult to make both sparse. I think a cool hypothesis is that I guess if you make the networks a lot larger, you can also get away with a lot more sparsity, and maybe then that's how we get a bit closer to the brain, because it's also very large and very sparse and so on. But yeah, so I don't have any work to present here, just like questions basically, and yeah, then some projects ideas. I don't know.
About activation sparsity.
Sorry?
Are there papers, how do they take advantage of activation sparsity?
You mean like the delta net
Or is there
sparsity?
anything
Yeah,
to-
temporal sparsity.
It's just sparse, it's good, or.
You can encourage it, you can try to encourage it with inner loss function to make the changes slower.
You mean on the hardware, like how to get it more efficient, like to reduce the operations? So it depends on the hardware. I think on GPU it's a bit hard because you need structured sparsity to take advantage of this. There are some papers that are looking into this, but on neuromorphic hardware, like I mean, right now I work with Luigi, and in Luigi, if a neuron doesn't get an event, a spike incoming, it just doesn't do any computation. So that already.
Can I say a few words about this activation sparsity for the dynamical system?
Yeah, of course.
Because like I think I just want to say two things. Can you go back to the Becky Glass thing?
Oh yes.
Right. Because I just think there are two things to say about the activation sparsity, right? Because I think one is that I find this really cool because you can go into the continuous domain now, right? Like then we have neuromorphics, right? And so the tradition I come from, which I'm more than happy to send you papers about, is called scale-space theory, where you can imagine that you can represent signals at different scales. Steve is laughing because I think this might be like the 500th time I've got this note. But I just find it really cool because that's exactly what happens in physical neurons, right? And so we have a paper showing that this is exactly what you get when you have leaky integrators, right? And then we have a neuromorphic network. And the second thing, back to your point about quantizing the activation, right? This is exactly what spiking neurons do, right? And this kind of theory, right, you get a sense how the very few bits have a meaning, right? They have a very certain spatial temporal perceptive field, which is what then the bits, the spikes will represent. Right? So I know I'm answering a question in a roundabout way, but I think what's cool about the quantization project here, and maybe we shouldn't go through the plot, but we can show that with very few bits you can actually retain a lot of complexity because you have this kind of sub-threshold dynamic. Yeah, sorry.
Are you doing this quantization to int like fixed point because of low ET? Because if you're gonna roll out an ASIC, you know, it makes sense to use some kind of low precision floating point.
Yeah,
Because
you
low
could
precision
do it,
floating
yeah.
point is hardly more expensive than low precision int.
Yeah.
You know, you get immensely more dynamic range.
From a implementation, hardware implementation point of view, the floating point is always going to painful, the fixed point. Just from a gate count point of view.
Why is it when Synopsys can give you the multiplier?
Synopsys can give you great multipliers, but in floating point, you've got to deal with all the other cases, the NANDs, the foreign cases that only exist in floating point. NAND only exists in the concept of floating point, doesn't exist in fixed points. Fixed point is always easier. Very straightforward as your circuit.
And fixed point by as well.
Yeah,
What's the
It's
largest
not a sensible representation to have.
LLM type thing which has
Doesn't
been
make sense.
trained with an
When
SSM?
your Signals are
the
spread. over
largest,
dynamic range.
so there's the Mamba models, they have, the largest one I think is 2.8 billion parameters. And recurrent Gemma, do people from Google know?
I think there are a few versions.
Like the largest one is also a couple billion.
Smallest one is 2 billion, yeah,
Okay.
7 something.
7, yeah,
But they try to push the smaller models to work.
yeah, yeah,
The 7 billion,
How much?
9 billion.
9.
No, but wait a
9
minute.
billion.
For
and
floating
the
point,
performance wise, it is comparable to the 7 billion parameter.
Yeah, I'm not sure, like the evals for recurrent Gemma and Gemma, I think they're not super different, right? Like,
They're not super different, but the current is a bit lower.
yeah, recurrent is still a bit lower, but much more efficient. Yeah.
Did you also quantize your state?
So, sorry?
Adjust A and B.
Yeah, so in this paper, we quantize everything, so we do weights to 8 bits, activations to 8 bits, and that works super well, and then everything is quantized. But yeah, as soon as we push the A matrix, the weights of the A matrix below 8-bit, then we get super high, like even with quantization we're training, it starts to get very finicky to get it to actually converge to a bit accuracy.
Yep, I still think that you should expose a low precision floating point because you don't have to worry about NANDs unless you do divides. You never get a NAND from a multiply.
Yeah, like, you know,
So
Yeah, so I think it's
you got your budget.
just from a viewpoint of representing signals, you know, floating point makes more sense because it's more efficient than using a bit. So that in any dynamic range, you have the equal precision.
yeah, when you get down to smaller.
I mean, that there are
precision,
spatial.
the amount you're spending on the exponent.
But it's not HGR that you're.
So
Maybe so,
it's quite all.
but it's a more sensible representation for things that have a big dynamic range, right? Obviously,
When you've got the ability to express it, don't FP4.
I'm glad.
yeah, that's true.
FP4, FP8, yeah.
Blame for an 8 or something.
Is the base around in the circuit.
Okay, anyway, thank you for this.
But yeah, thanks for listening. Here are some like projects. They're not complete because I missed the first week, so I don't know actually what's going on, but these are some things that would be cool to work on, so. Yeah. State tubes are cool. So yeah, join I think there's an SSM channel, you can join that, and yeah, happy to talk more about all of this.
It's a lack of time. Yeah. Let's try to.
So ultimately, you end up with this big array of now 500 designs, and you're addressing into, once you manufacture it, you're able to address into one of those designs. You just enable your slot, and then you can play around with it. Something like 8 inputs, 8 outputs, and 8 programmable IOs, where you decide whether it's going to be an input or an output. And I'll show you how to program that briefly. This is what your GDS file is going to look like. So the final thing that ends up getting manufactured. Oh. Yeah, so that there. You're going to write a bunch of Verilog that describes your circuit. That gets synthesized into a bunch of transistors and metal wires, and that's the thing that you're ultimately going to end up playing with.
So this is only for digital, right?
It used to be digital only. As of this last run, analog has been enabled as well. So Ray was actually one of the first people to mess around with the analog flow. So he's going to be I haven't gone through the analog flow myself. It is a bit more expensive, and I believe that you're expected to kind of chain together multiple tiles. So that is one thing that's kind of cool, because there's your chip is partitioned into 500 different little mini slots. You can chain them together, pay a little bit extra, it's not much, on the order of like $100, and you can take more space for a larger design. So last year I did a Hodgkin-Huxley neuron and kept in a bunch of exponentials and whatnot, and so I needed to thread like 4 of the slots together to make that fit. Designing that took me like 2 hours, and it was super easy. Kind of made the whole the back end flow is very much hidden from you, so you're just focusing on Verilog. You don't have much control over timing, finding critical parts or anything like that. Everything is done through GitHub Actions. So I'll go ahead and show you what this kind of looks like.
Quickly, is it possible to get separate chips to talk to each other?
Is it possible to get separate chips to talk to each other? I don't think so.
So you can only do one.
It's a cool idea, but yeah, I don't think so. No, not from our abstraction.
Wondering if we could game the system and get multiple slots.
So no, okay, right. So you tell them that you want to reserve 1 slot, or chain 2 slots together, or chain 2x4 slots together, or 2x8 slots together. Last I checked, I think 2x8 was the largest that you could get. Yep. So you don't need to game it. They kind of have it there as an option. Right.
You can also, I mean, you can put IOs on there. It's just you're limited to, I think, 60 autologous.
Yeah, that's what I'm thinking. You want to get away from being IO bound.
Yeah, I mean, you can put an 8-bit bus, for example, on there.
Because that's, when you're that small, the ratio of the area that's occupied by IO pads versus logic pads is terrible.
I mean, the pads are.
They're fixed, right?
In your little slot.
Yeah, it's not.
Sorry, let me rephrase. IO circuitry.
Yeah.
So the deadline for the 8th iteration of Tiny Tapeout is in 2 months. In order to get started, then they have 2 options for design. I would encourage everyone to take the Verilog route, but there is this thing called Blockwe, which is a graphical interface type editor. So for advanced users in HTML, let's see. So I'm going to click that, HTML templates. So you want to open up this GitHub repo for Tiny Tapeout 8, and I minimize that.
Source, right?
Come again?
Source.
Source, yep. So SRC is going to contain all of your Verilog files, but before you kind of go ahead and mess with this, you want to go ahead and click use this template, create a new repo, give it your own unique identifier, say LIF, which is integrated via neuron. Maybe I'll start it with TT, but Tiny Tapeout. Create a repository. And so
It has to be public, I think.
it has to be
It
public.
has to be public, otherwise it doesn't work, and they also have that submitted.
Yep. So from here, what I would personally do is clone this repo locally so that you can mess around with things on your own browser, test things. I'll give you a high level view of what that looks like. Probably won't go through it myself because it would just take too much time. But I do have some documentation that I've uploaded to the Slack that you can use. See, all of these flags are grayed out. So let's go ahead and open up the Slack. 24. I put these instructions for the 5th Tiny Tapeout. So things have changed a little bit since then, but I think it's pretty easy to fill in the gaps as to what is new and what you don't need to do. So create fork, which was basically the equivalent of using this template now. Enable GitHub Actions by clicking on settings, pages, deploy from branch to see if I can remember all of those settings, pages, deploy from branch. Yeah, let's just do that. Hopefully that works. I think I have to do the same for actions. Allow all actions and workflows. So yeah, this has changed a fair bit since the last time I looked, but I think it's fine. All right. Now, if I was to go ahead and clone this repo. So let's go to here. So I'm going to git clone, copy paste that URL. All of these instructions are available. named it TT_IF. Go ahead and open this up, the S code. I'm getting a lot of lag. So let's take a look at what this folder structure is. I don't know if we can read.
It's use control plus to zoom everything out.
Perfect. So there's a few things that we want to look at. Source, that's where a lot of all your primary project files are going to be. You can see project.b, let's get a sense of what's going on.
It's top, that's the top.
That's the top, that's your top level module. So it's going to be named, all project names, I believe, need to start off with TT_UM_ whatever you want. You can see that you have 8 dedicated inputs, you have 8 dedicated outputs. These two, they're reconfigurable. So they're still addressing to the same paths. So you've got 8 UIO_in and 8 UIO_out. Those two things address to the same paths, and you choose whether they're going to be inputs or outputs using this. So if you force this variable UIO_OE to be 0, then it's going to read in from your input. If you set it high, then it's going to read in for it's going to push those values as an output. And I think this is just some simple little test case. You have to make sure that all of your output pins are assigned. If you're not using them, force them to 0. Otherwise, you are going to get errors. And you're able to create new folders, new files within here. So let's say that I actually just want to integrate via I'll do that later, but let's go through the tests as well. There's also this makefile folder. I think the only thing that you really need to change is, so this might actually be done automatically now. So you don't want to change much at all. I think all of this needs to be fixed.
The top level module for
Top.
I'm gonna take that B, right?
Now this is changed. So we want to keep Verilog sources. As you can see, the test vector bench doesn't change. In the past, you would have to just chain together every single .v file, so that when you push this repo back to GitHub, you're triggering a bunch of actions. Those actions are going to run your tests. So we have tests for this. It's going to run synthesis to turn your Verilog, your code, into some physical structure. That's all going to happen online in GitHub's cloud. And there's a third action, which I don't remember. Paula, do you remember what that third action is?
Actually, now there are 4 actions.
Oh, there's 4 actions. Oh, documentation.
And
Oh,
another
cool.
one
Yeah. Why would they do that? Okay.
Plus of the function.
Right. Okay. Interesting.
Hey, Jason, I got a question. So, yeah, can you hear me?
Yep.
Yep. So Abreu told me there's no support for VHDL. Can you confirm or deny?
Say that again.
I said Abreu told me there's no support for VHDL. Can you confirm or deny?
There's a what DSP?
The support for VHDL.
Oh, for VHDL.
Yep.
There is now.
I am not sure, but now.
One second,
the
please.
option, now there is the option to show VHDL. I have to try, but there are some design that use VHDL.
Well, not HLS, right?
Not HLS, no. So Quasi Paula says that there are some designs out there with VHDL. We haven't verified. I've never tested it.
In the template, there is a bit.
Yeah.
If you go in the template for the times about
Oh, so there is an option for VHDL.
Yeah, there are Verilog and
VHDL. Okay, so yeah, we believe that there is an option for VHDL.
Nice. That's awesome. Thank you.
What about memory?
What about memory? No.
No SRAM, no SRAM.
No SRAM.
Register memory, basically, that's it.
Yeah, whatever registers you can throw on there yourself, that's what you're stuck with, more or less.
Also systems are evolving.
I don't think system Verilog, last I checked, it wasn't supported.
It is partially supported, it's a pain in the ass, so maybe
What did you say?
system Verilog is only partially.
So system Verilog is only partially supported.
So- No, because it's not synthesizable, right? Yeah, so that's what.
Cat
The
thing.
system Verilog is synthesizable.
Yeah, those are even Verilog.
Even the synthesizable subset of system Verilog is not fully supported.
Yeah, that's
Because
correct.
it's using open lane stuff in the background that has some issues.
Yeah. Which that's probably the most frustrating thing to me. Toby mentioned,
Jason,
yeah,
Yeah.
Andreas.
sorry guys, I came home. Going back to the SRAM question, but I think one could create SRAM blocks of certain size and import the GTS or in the process. Can you do that? So let's say
if you wanted SRAM that, okay, so you can't lay out SRAM that breaks DRC, you have to have DRC passing. You can lay out your own custom SRAM that would qualify as an analog design. And you've got to specify that you're going to be doing an analog design.
I see. Okay, yeah.
Yeah, I don't think you can do cross-coupled inverters digitally without running into
I see.
an error.
Kind of maybe this was on what Andreas was thinking of, can you do like a mixed signal design? So I'll do like an analog block and put a little bit of digital around it.
Yeah.
Like with the PNR flow.
Ray did that, yeah.
Yeah.
Ray had a bunch of DACs, yeah, he had 3 DACs and some amplifier in there.
There are already some design that you can find the technical step.
Yeah.
I'll
I'll probably actually show you, the best way to if you're really unsure about how to approach this, the best thing to do is go and see what designs are on there, see their folder structures, and just starting with that as a base.
So how do you see all the designs that are open?
Let's find out. So
And how hard is it to look at it?
very easy. So everyone's had to push their designs to GitHub, which has the same template. So you know all their Verilog files are in SRC, you can see their tests. I should note that there is no all you have to do is write tests that pass. So you could have a bunch of floppy tests that mean nothing and pass. Bad practice, but that's you can do that. Let's see. So let me kind of wing it here. Tiny tapeout chips. Okay, perfect. So TT, what did we do at Telluride last year? TT05, right?
Yes.
Okay, and then subsequently we had 06. I think 06 is where we had a ton of okay, so I'm not on that. So it was TT05. Yeah, cool. Okay. Chunky spike in here on that. Okay, so I'll open my Hodgkin neuron. So I just added in a bunch of documentation and specified the IOs. This tells me where that chip location is. So I brought out that little chunk there. And the GitHub. Let me find another design that is simpler to follow. So yeah, everything will have this GitHub repository there, and you can just use that.
And how do you run all these tools through GitHub or?
Yeah, every time you push, so once you've enabled the action workflow, you push to GitHub, and then you go into actions, and then it's going to run these automatically. Don't path it around. Yeah.
So you do all synthesis PNR here.
Yeah, everything goes. So I can try and, rather than doing it myself, I can try and find something that I pushed a while ago and show you how that works. Is there a question?
Yeah, so you got an analog designer, or is that basically what it was?
TTO, no, that TTO5 is purely digital. So I haven't played with the analog flow on this yet. Ray has, so we're able to look at what he's done as well.
Because to that point about mixed signal, perhaps you could even explore balanced toner.
Yeah, absolutely. No, we can definitely play around with those weird and exotic things now. So yeah, this is just a simple integrate and fire neuron. We did this in my brain-inspired machine learning class. I basically used Telluride 23 as a experiment, see how easy it is to get people that don't know how to do chips to, I guess, run tiny tapeout. It's super easy. Did it with a class of 31 or so students that had never touched silicon before. So these are passing, that's all well and good. Let's look at the folder structure for Asculus design. So SR in source, let's go into, we don't want to touch cells. We've got IF underscore neuron, and then we've got our top level module. So really, we've only got two files here that we really care about, IF neuron and the top level. The IF neuron looks something like this. I'm not going to code it from scratch this time, last year. Current injection, you've got a clock, you've got active load reset, output spike, and let's also probe the state of the neuron. So this is just a single integrated fine neuron, very vanilla. You can go through it. If you're uncomfortable with Verilog, ChatGPT can do very basic constructs. Like
on like kind of the IO side, how much control do you have while you're testing? Can you turn the clock off, stuff like that? Is this often like a microcontroller or?
My feeling is that, okay, so your clock is your clock. You're going to have a clock streamed into your
I can't turn it off.
design. I don't think you can turn it off. You can always just not use it.
Well, more so for like, say you have clocked inputs, you have to worry about like metastability synchronizers and stuff like that.
Yeah, okay, so my cost, if you have clocked inputs, then do you need to worry about metastability and synchronizers? Sure. The specs of this, so I don't remember off the top of my head anymore. What was the maximum clock speed? Do you remember 30 megahertz or something? 50 megahertz? Now, take that with a pinch of salt. 66 megahertz, but yeah, take that with a pinch of salt, because I feel like there was a mismatch between what the microcontroller that was controlling the chip had, the speed at which the microcontroller could run at, and the chip itself. So I think 66 megahertz.
To buy a generic board for testing this chip?
They provide everything.
This is the one that's mass produced by them,
Yeah.
this motherboard, and then you have to design this daughter board?
No, they provide everything.
This comes to you. and
That
a few
comes
of
to you.
these.
Yeah.
One of these and a few of the top board.
Yeah, and basically the test platform is basically a Nucleo 64 based STM M7 microcontroller.
That you program in Arduino?
You program either in the whatever. No, you program in ST Max, whatever the standard tools that we use, the MX.
What is that? TTO4?
Cube, ST Cube MX.
Okay, so sorry, what was that? It says 4 on it. 4, yeah, okay, so that's 4. 5 is currently being shipped. Ray and I asked to have 5 of them sent over here so that we could see the Telluride designs and all of the, we flooded that chip. So at the time, there were 250 slots. We took over 50 of them. And yeah, so a bunch of weird random things.
One did it?
I don't know the latest costing, but when I did it for TTO5, $50 to reserve just one slot. And then that scales linearly if you want to chain extra slots, and then $50 extra for a board. Now that price has gone up because demand has gone up. Analog is a little bit more. And I think that you need to pay a little bit extra on top. Well, we're talking in the low hundreds if you want to use analog pins and stuff like that. So if you need like 3 analog pins, that's going to be cheaper than 4 analog pins. I'm not completely sure. I haven't looked into it.
Basically zero compared to like 10K, that is like the minimum chip cost.
Yeah.
You know?
It's the initiative, it's a wonderful thing in terms of just like a one-on-one education to get something physical in your hands. Testing. Let's briefly look at testing. I'm not going to go through the full flow, but this I can send this. Actually, I'll send it on the Slack now so you can take a look at this design. Testing. I think you have a few different options. Coco TV is what I've played with, so I would just go with that.
But you use a standard Python test bench or something?
Yeah. Coco TV is a
unit
Python
test, Python unit test?
Yep. Sure. Python unit test. Now so Coco TV does interface with this Verilog file, which we don't need to touch, I believe. Yeah. It's all good. We don't need to touch that as long as you don't change the names of your pins, which you shouldn't be. The top level pins. So if we open up test.py here, then you can read a pretty janky test, but it's okay. We're just applying a constant current. I guess that the input bit width is 80, so it's 8 bits, so we've got a maximum of 250, 0 to 255. So we're just arbitrarily setting a constant current of 50 and seeing what the waveform looks like in response to that. We apply a clock. We got where we're running at 1 megahertz. Gigahertz.
That's the fast.
I guess it's all abstract anyway, because when you're testing, you're just doing functional tests. You're not actually getting any sort of physical level, so it means nothing. So then we reset the circuit.
Yeah, but you can go there, so this is the first one. Yeah, you can do that also, implementation.
Right. So yeah, we wait 10 cycles. So this is all just sequential now. We wait 10 cycles. We take the chip out of reset. Remember, it's an active low reset. You have to enable your design by setting this variable design on test .ena .value. So we're indexing into ENA, setting it to 1 to activate your specific design. We run for 100 clock cycles. There's various syntax that you could use, and ChatGPT is pretty good at writing very simple tests for this as well. I guess during this phase between cycles 50 to 80, we are applying some off current, and we're applying the high current outside of that, very arbitrary. But I think the point here was just to see the membrane potential kind of going up exponentially, spiking and resetting. It's an integrated bias, so we just kind of go up, spiking, and then actually be able to use GTK wave in order to see what that looks like. Bit of a sanity check.
But you also have TV.V, right? That's a very long test method. This is the final test.
Yeah, so
what is the difference?
The two, they interface with each other. Yeah, because this test.py doesn't have any info on what your pins are.
Right.
So there are a bunch of files in the background.
So it will internally call TV.v?
Yeah, I'm not sure if it's in the make file. I haven't looked into the
Yeah.
TV.v. No, so I opened that already. So something's got to be interfaced with that Python file. I'm not sure what it is. It could be your. I'm not sure.
So in the make file, you specify what the top level test bench is, and then the make will basically run some simulator. I think here it's Icarus. You can change it, like Abreu can change it to their data, for example.
Yeah.
And then it talks to the simulator and basically pauses execution whenever you have an await statement in Python. You can set some wires to new values, and you step through the simulation basically. It's just Python is controlling the simulator.
Yep.
Pretty nice, actually.
Yeah. Yeah, the syntax, don't take this with a pinch of salt again, because the syntax and the way that files are structured have changed a little bit. So this is from TT05. So all of the relevant .v Verilog files are just listed here, but it seems like there's been a bit of a change since.
Anyway, it doesn't matter.
Doesn't matter.
So, Jason, maybe Paula also can give a follow-up little tutorial on the last one, which the last one was TT6 or what?
No, we're up to TT08.
Paula, what did you tape out?
TT6.
They didn't
But the
analog.
last one is
7. So 7 when analog started. Yeah.
Okay. Yeah, but this is it. You have to follow the instruction, implementation. Yeah, it's pretty simple.
Yeah. So
how do you run that simulation that you showed there?
Yeah. Okay. So I won't do it, but here's a sense of what you would do. I would go. So you got to install pip install CocoaTB. I would go ahead and run Python test.py. That's going to automatically generate is the BCD file, which contains all your waveforms, and then I open up.
And Icarus, the simulator, is it installed automatically on Git? Where does it run?
You have to install that locally. I have instructions.
I see. Okay, but you can also use anything else for simulation.
Oh yeah, it does.
Behavioral simulation, right?
Yeah, with what you run in Git, you don't get, I'm not sure you can, oh yeah, it does generate a BCD file that you can download, yeah, you're right. Yeah, I forgot about that. Yeah, so every time you go git push, then in your action, you can open up your workflows, you would just open up the relevant, before you're gonna resimulate, hopefully they pass, quite often they fail, you gotta go through a few iterations of debugging. It's going to generate a bunch of files. Let's actually open up this one. Okay, so this is what the waveform looks like. You've got your memory potentially at the state going up, and then you get a spike, keeps going, and then we have that phase of off current. So it seems to be doing the bare minimum that we asked it to do. This is what some of this looks like. So we have testing, GDS, and docs. Let's open up all of these. So GDS. That's expired, so I can't look at it. Now, when you push, you're able to open up, I forget what you're meant to click, GDS or viewer, but it will show you the GDS file, which is really neat. You can also, there is a 3D waveform viewer as well. That looks very cool. This is your BCD dump. You can download that and just drag and drop it into GTK Wave. GTK Wave is an open source waveform viewer. I think they recently made it, enabled it for MacBooks as well. I think this was like late last year, so it's really recent. But it doesn't work with old Mac OSs, maybe not the recent ones. So I'm not, yeah. If you have issues.
So it does work. I've tried it.
Oh, it does work. Okay.
Yeah.
There you go. I also have Dockers. Where are the Dockers? I provide links to the Dockers in the PDF file, which come pre-installed with GTK Wave, pre-installed with whatever prerequisites that you need. So just go through these instructions and hopefully there's not too much of a mismatch. You can follow that. I think that's it. Once you git push, then if you actually want to go ahead and submit the design, you need to make sure all of the actions are passing first of all, but then you would also go into tiny tapeout. Let's see. So they listed UC Santa Cruz because I've given them enough money.
What was that prices up above there, those dollars?
So I think that's for classes. So small class, 5 projects, PCB kit.
I see. It's cool.
So yeah, when I ran this, it was really easy to run with like 30-something students. Yeah, it was smooth, and it was a great way to get undergrads into chip design.
But it's a good point though, like we should get a sort of, like not now, but like count how many projects people are actually interested in doing it. Maybe just do this because it's cheaper than individuals, right?
But then you only get 3 PCB kits, and I think that everyone should get their own PCB.
Well, that's it.
What is the customized plan? Maybe they can.
We can look at this later.
Yeah,
It's cheap enough for it to not matter, I think.
$250 per PCB.
250 per PCB. Damn, they cranked it up.
3 quantities, that's $750.
Yeah. I guess the demand went up.
Really targeting, it's really targeting outsiders and beginners.
Yeah, this is outsiders and beginners for sure. This is not for pros. So if you are a pro and you do want to go through the open lane flow locally, then just go open lane, read the talks.
So what would be the advantage of that? Yeah, you could do mixed signal.
So this is if you want to go through the full open source, open lane, open road flow and just take a whole die for yourself. This is no longer what I've now opened up is not tiny tapeout. They do use open lane in synthesizing your design, but it's like there's a harness and you're constrained to one slot. Your slot is the die. So it's kind of 2 different pathways. And if you're a designer that actually wants to do something real and not just get educated, then you would install open lane locally, you would Verilog, you would just go through the typical flow and yeah, just go through.
But you still need to make your own SRAM, right?
So
SRAMs, yeah.
you could make your own SRAMs. You could use the macros that are provided by OpenRAM. I should say OpenRAM isn't as marketed as a memory compiler, and it is. It's just that you can't parameterize everything and expect timing to check out. It does not. So you just got to go with things that have been tested. Whatever.
So just,
Yeah.
I'm agreeing with you.
Perfect.
No, I was agreeing with that because it is, the open RAM is,
Half-assed memory compiler time.
it kind of works, but
Yeah.
yeah, it only works under, but it's only verified for certain sizes.
Yeah.
Of course. But if you're, those sizes are lots of those sizes, it's there.
Yes, I mean, for example, do they have dual port SRAM or is
Yeah.
it just your very basic?
They have both single point and dual point SRAM, yeah.
The thing to understand also, take, I think it's true for the tiny tape, tiny ones, well, there's actually, you know, the core processor on the die is a RISC-V.
Yes.
And so
But
there's a risk,
you're no longer forced to have them. So previously,
Right, you didn't have-
you had a harness with SRAM forced upon you, with iOS forced upon you, this
Right.
wishbone bus firmware that you could
Right.
load and risk. It used to be a Pico RB32 processor.
oh, yes, that's right.
Now that's
right,
changed
that's
to
right.
another
Well,
RISC one.
What was a RISC-V?
They're just, they're all risk variants. of
Yeah,
RISC-V,
it was, yeah, but you're correct.
Yeah.
Is it
And
under
and it came
That's
with
the
that,
Paragon.
with two KS RAM on it.
Right.
So that's what you had on four of the harness,
Yep.
Caravelle harnesses.
But in the past 12 months, they've finally given the option to get rid of that harness, that pad frame with the extra bits and pieces, since and at the same time, they're allowed for analog designs. It doesn't make sense to have that harness. for
What's the
analog.
typical turnaround on these runs, like, what goes back?
Pardon me. That changes a lot. It's very.
1 year.
1 year, it's,
We got it in 3 months.
you got it in 3 months.
Yeah, you pay for it.
You pay for it. So was this,
Yeah, you
this
pay
wasn't a
for
tiny tape out?
No,
it was
they
a-
opened.
You have to pay
Okay.
for it.
So that was 3 months then.
Not bad.
Between 3 months and a year.
Yes, it's
So how much extra to get faster in 3 weeks?
It's different if you're doing like
10K
overlay
or 10K.
So we talked about 10K, so it's no
Yeah, 10K
So
a run.
for a full.
Yeah, there was some, they have some bugs.
Yeah, so
they keep.
Yeah, the first 5 FPWs had issues. I think I was the first one that didn't have issues in FPW6.
I can agree with you with the first 5 issues.
Yeah.
Issues with the fab itself,
With
or the pads.
It was with the pads and with the digital design.
The
and
models.
synthesis. So
Yeah.
it turned out the first design, if you actually use any of the IO pads.
Say that again so I can relay this.
So for the first design, if you had any IO pads, they were basically, you couldn't actually get out the IO pads because they actually had. a
So the
flag
first design, you couldn't
on the-
extract signals
on
from
the
the IO pads.
Processor control. They have many other bugs along the way, including, they have a really nice sort of digital, structure to kind of put data into the system, right?
Yeah.
Basically, 128, yes, a bus coming in off the processor. But their documentation swapped for this.
Okay,
We got burned on one of those. So that was great.
Yeah.
sounds like you have a lot of experience already.
Yeah.
We have data. So, we've had
Yeah.
some work.
I should mention in terms of,
The whole thing works, I can definitely show you that.
in terms of memories and whatnot, it is pretty janky and finicky, but my colleague Matt Goodhouse did. So if we need hands-on support in that, this student's down for
Quick question,
always
because
from me.
everyone is complaining about how bad the status there is, like, how much effort is it to fix stuff there? Is it something where everyone just complains and no one wants to do it, but it would be like 2 days of work, or is it
Yes.
something that would be like years
Yeah.
of work?
Exactly that. It's just several days of effort that's needed, but when was the last fucking time we had several days of free time? That's it.
Someone should.
Someone should, yeah.
Well, and to be fair,
Also, if you go to the open lane, I suggest that you pay whatever little fee there is.